Okay, thank you very much. And I hope that Piotr is hearing us also today. So, Code Dive. Very special event, sixth time. And always bringing a lot of the nice speeches. We have speakers from Nokia, we have speakers around the world, as Rafa already was mentioning. But as usual, at the opening, I would like to really mention, how the Code Dive is built. Okay, thank you very much. And I hope this is not the hearing us also event that Nokia is buying from the other company, from the some agency or the people from the external are behind that. Sixth time. So everything is coming from the bottom up. So there are passionate people who are working on the Code Dive for the full year, thinking who should be coming and what there should be the topics. A lot of the passionate people are delivering this to you. But I would like to really thank with the names of the Adam, Marcin and Michał, who are really behind the conference this year. And I would like to have a big applause for all of the people who are behind the Code Dive. So big applause, please. Whenever I was thinking about the Code Dive, this is, one of the base for the first Code Dive was that to build a platform for the Wrocław IT community, that then, of course, it was extended to the other sites and the other places, but the platform in which you are able to have a really good technical talks. And this is working very nice. But then, you have some gift coming out from the Code Dive that, you can refer to the YouTube videos with the lectures, but then we were also thinking, how to take the Code Dive into the packet. And one of the really, nice thing which we are also doing in Nokia, in Wrocław, is this book. It's called the Nokia book. And this is quite, fat book that you have plenty of the pages of the technology. We are releasing this every year. So this what you are seeing is the 4th edition and the 5th edition is just coming. But, the engineers from the Nokia writing the articles, I would say about the cutting edge technology. Many of the articles that the people are putting in this book are not able to be found anywhere. The universities are coming for us, to get these books. And, this is very something which was also coming from the spirit of the Code Dive. So I really encourage you that whenever you are finishing these really fruitful 2 days, you will be having plenty of the talks, you will be having plenty of the discussions, which is really, really important. Do not forget also about that there is a Code Dive in the packet, which is called Nokia book. And you can download the versions, electrical versions from the internet, from the GitHub, where all of the books are storing. And the last but not least is that, it's coming the 5th edition of the book very soon. It's talking everything about the machine learning. So if you are interested, just stay tuned up for this release, which will be coming very soon. So just to making the closing, I really wish you the very fruitful 2 days, good discussions, and I wish you enjoying the Code Dive. So thanks very much.
Thank you, Bartosz. So, time for our first talk of the day, and it will be delivered by Barbara Geller and Ansel Zemmersheim. Barbara's primary work involves software development.
Hello. Hello, ladies and gentlemen. On that fine evening, my name is Jarosław Freus, and I will be host for today's Stage 9. I hope that you have had a chance to grab a coffee and be fully awake. If not, after this lecture, there will be a 30-minute break for another coffee, so you can enjoy it. I would like to mention some rules first. Please put your phones into silent mode, and not to disturb other viewers and the speaker. Please don't leave the room during the lecture. And if you have a question, you can give it to Brandon after the lecture outside of the room, because Brandon has a lot of material to share you with, so there will be no time for questions here. Our first speaker is Brandon Rhodes, and you most probably read on our Code Dive page his technical bio. Privately, Brandon likes hiking, and most probably his next trip will be the Grand Canyon in Arizona, but I must say that we have quite nice hiking trails 2 hours drive from Wrocław. So I have a question for you. Have you ever considered Poland as a hiking destination? Please welcome on stage Brandon Rhodes with his speech, When the Python Practices Go Wrong.
Testing. Good morning. Thank you for the welcome, and thank you to the conference organizers for having me. I love visiting Wrocław, and I like talking to your community. This is my talk, When Python Practices Go Wrong. I'm not going to talk about Python, the language, and its features that might have been good ideas or might have been bad ones this morning. That's a different topic, and it's also one that we can't do very much about. Once features have been added to the language, they tend to stay. But it can be very impactful to study our practices around how we use the language, because those are flexible and continue to evolve. So I'm going to discuss 4 different areas of Python practice today. I'll start with something relatively uncontroversial to get us started and look how the community has learned the good and bad aspects of using that part of the language. And then I'll finish out with 3 topics where my ideas are a little more controversial, because I think the community still has some things to learn and still has some practices to perfect in some other areas. So let's get started. My first topic is compiling new code at runtime. Python has, they're slightly different, an exec statement and an eval function, as do many dynamic languages, which let you get a string at runtime that contains some code that was not available to the compiler when your modules were loading. You get that fresh string, you send it to eval, it is lexed into tokens, it is parsed into an AST, it is compiled to bytecode, and it is run. The entire string to compilation process runs afresh for the string that you pass so that the code can run and produce a result. This isn't available in languages where the compiler is gone by the time your application is up and running. It is a feature of dynamic languages that compiling novel code in the middle of your application is possible. But is it a good idea? Some beginners to a language like Python start using eval for any dynamic operation they can think of. They think, I need to get an attribute whose name I don't know until runtime. Maybe the user is selecting from a menu, and that is when you learn what attribute you will need to display. Such programmers, when they are beginning, think that they need to go through that entire compilation process in order to say my object dot and the attribute name. Because many early languages were called dynamic merely because they offered eval. They were dynamic purely textually, in the sense that you could construct new phrases in the language at runtime. But Python is more powerful than that. Python is dynamic because it offers introspection and data-driven object operations without making you build strings and recompile them using eval. Instead, for example, in this case, there is a getAttr built in that lets an attribute whose name you have just learned is a string be looked up at runtime without going through an entire compilation process. So we steer new programmers in Python away from eval because for whatever dynamic operation they want to do, whatever introspection they want to do, a better mechanism than eval is almost always available. So how does eval wind up getting used? Eval wound up having a great future. It's widely used in the language today. It's just not where we first expected it. For example, you can go look in the standard library. You will find that we have in the language a class factory. It's a function that you call, and that gives you a new class every time you call it. You tell the language that you want an immutable struct, a named tuple it's called. You tell it the class name, you tell it the list of attributes that you want it to have, and it generates for you a convenient class that takes all of those attributes at instantiation time and then can let you access them later. Wow, Python builds classes at runtime. How does it do that? If you look under the covers, it's using exec on a string. It is not painstakingly going through by little bitty steps and building up a type object manually. No, it just builds a big string, which is the class statement that it wishes that it had at load time, and it runs it with exec, and out comes the class that it wants to return to you. In fact, this bothered some people. A contributor once got on the Python bug tracker and offered an alternative that instead builds the named tuple class without using exec, without recompiling a whole string from scratch. The core developers turned it down. They had tried that before themselves, it turned out, and running the string was faster. Python is pretty efficient at running Python. And they found it was easier to get correct. The class statement built a class that was perfect, whereas if they tried to use little introspection operations to build it, it was easy to get something wrong or incomplete. So, templating types was judged in the standard library to be a legitimate use of eval. Another use is called doc tests. Documentation often, in many languages, includes sample code. Maybe your README shows what looks like a little Python prompt with an expression that produces a result. Very often inside of the doc strings that we try to remember to put at the top of classes and functions and methods, we might also illustrate, because very often it's easier to understand an illustration of what something does than a textual explanation. Show instead of tell. Someone seeing these examples once thought, well, what if we could execute? What if we could run the code inside of the documentation? Then we could see whether the output still matches what we claimed the code does in the documentation. And thanks to eval, it's something that you can write yourself. I mean, don't try. There are some edge cases that are a bit sharp. But the basic idea is just go through the text, and any lines that start with what looks like a Python prompt can be evaled, turned into a repr, and compared with the next line in the file and what it claims should come out when that expression is entered. This became, in the standard library, the doc tests module, a standard way that Python programmers keep their documentation in sync with their code. Now, we did have some learning to do. There were some downsides. Some people started trying to write all of their tests as doc tests, and there were some problems. It meant then, as they wrote a huge text file to have all of their tests, that the code snippets were all coupled. A mistake at the top would break everything else, even if those later features in your class were really working. It was just awkward documentation. It would start explaining how the function works, and then would start talking about all of these edge cases that you didn't really care about. You realize they were talking about them because they needed them tested, not because they were really interesting to you. And so they didn't wind up being a good model for real tests, but a great, great tool if you keep it limited to testing documentation. But we had to learn where that mechanism, based on eval, was useful and where it was not. But what was the greatest success of all of eval? It has to be the IPython notebook, the Jupyter notebook, as it's now called. This was easy. I believe the project was started by a scientist. Python makes programming that easy. They wrote a loop that takes input, initially at a prompt, but now also in cells in the browser. It runs eval on the code that you've sent in and can send back graphics, images, charts, data tables, and raw Python output in an interactive display that lets you, instead of running your statistics analysis program in one shot, it lets you load up the data and then work with it live. An ability powered by eval that is making Python the tool of choice for statisticians, scientists, and data people all around the world today. Possible, not just possible, but easy for someone to get started implementing because Python is dynamic. Eval, turns out, wound up having only limited use for application code. I write thousands of lines of Python without ever running eval. But it gets very wide use, usually not in our applications, except in name tuple, but in all of the tools we build around the code, the tests, the development environments, and the tools. I'm now going to go on, having used that as an example topic of how we learn as we work with a language over the years about what its features work well and work badly for. I'm now going to go on to a second topic. Let's talk for a minute about Python's object model, the way people use it. What is the object model? Well, Python has a number of operators that are supported by its built-in types. Ints and floats know how to do addition, subtraction, comparison, and other operations. But it's not only built-in types that get to be part of that ecosystem. Any class that you write in the Python language can opt into the same operators if it adds special methods that the language recognizes as special because they have double underscores at the beginning and end, like certain symbols in the C and C++ language that are special to the precompiler. We call these double underscore methods dunder methods, and they are the way that your classes, if you want, can support built-in Python operations and operators. Here are some ways that people have tried to use those. Let's look at 3 dunder methods. First, dunder bool. Dunder bool lets your object participate in if statements, while loops, and other built-in constructs that have to make decisions, true or false, based on a value. In Python, a value really means an object because everything in Python is an object, and your objects, by implementing the method dunder bool, can also be eligible to be the condition of an if statement or a while loop. Many built-in types have already opted into this system to make Python comfortable for C programmers, C++ programmers, and Java programmers. Integers declare themselves false if they are 0. Floats declare themselves false if they are 0. And all kinds of containers consider themselves false based on their length. They take their integer length as determining whether they are true or false. Programmers love brevity. I don't know if you've ever noticed this or tried to read the code of someone that tries to be very brief. But in no less an authority than PEP 8, the official standard for how we should write Python code, it says this: for sequences, strings, lists, tuples, when doing if tests and while loops, use the fact that empty sequences are false. What habit is this trying to encourage? It's trying to encourage this. A beginning programmer writes this: if the length of the sequence is greater than 0. But then they learn more about Python and they say, wait, 0 is already false. I don't have to compare myself to 0 if I want to skip the body of the if statement for a 0 value. All I have to say is if len of sequence. and it means the same thing. Then they learn a little more Python, and they realize, well, wait a minute, sequences already judge their own truth or falsehood by their length. I can just say if sequence. It's officially recommended in PEP 8, and it just makes developers feel good because it's fewer characters. Problem. And this is something I only really realized in the last year or two when working on very big code bases. Python code is always in danger of becoming a type desert. I mean, empty and barren wasteland, and the sun is beating down on you as you walk through the heat, thirsty for any knowledge of what types the variables are. This isn't so much a problem in smaller programs, but in a huge system, 100,000 lines of code, you can run across a routine like this and ask, what is the type of users? The only hint you are given is that it's used in an if statement. How much does that tell you? Almost nothing. Anything can have a dunder-bool method, because the object in an if statement can be anything. It could be a user collection that has defined a dunder-bool method. It could be a normal Python list, but of user objects. It could be a list of usernames. That could legitimately be called users. In fact, I've been in code where I suspected one of these things, added a debugging print statement, and found that users was 12. Some people don't always call that user count or number of users. They think users is clearly a number. It might not be clear to the reader 6 months later, or even to the author. In the Zen of Python, which I hope you have displayed on your screen as you sit with your tea or coffee in the morning and get ready to code Python, when you type import this, and the Zen of Python prints on your screen, you see that statement. Explicit is better than implicit. In Python code, where as systems become larger and larger, it's often a difficult question. What the type of a variable is might not be a good hint. I have found myself stepping back from that PEP 8 recommendation and keeping things explicit rather than implicit, making it clear to myself, giving myself a reminder whether the if statement is attempting to make a judgment on the size of a container or a judgment on the value of an integer. Those of you who have used the language will guess where I got this. Last year, I had to do some work on a code base that was in Go. Go does not believe in implicit trueness or falseness. You have to do the comparison. You have to show your work. When I came back to Python, the if statement almost looked unfinished when it just said if users. So I didn't tell anyone I'd just been using Go, but I wrote the if statement explicitly where I could see what it was testing, and I suddenly felt that more knowledge was being left in the code than when I omitted it. Don't tell anyone. Try it and see if it does the same thing for you. Maybe it will work, maybe it won't. But that's an area where I'm finding a common Python practice deprives my code of knowledge that maybe I'd prefer it retained. All right, a second part of the object model is called getAttr. This is a fallback for if you try to look at an attribute of an object that doesn't exist. If c.foo isn't there, but getAttr is defined, then you can have dynamic code that decides on the fly whether there is a foo attribute or not, either raises attribute error if it thinks it shouldn't exist, or returns a value for it. And a client can't easily tell the difference between whether that was a real attribute that was there already or whether you made it up on the fly. This powers some very important patterns. For instance, the proxy pattern in the Gang of 4, standard design pattern, if you are wrapping a class with 30 methods, traditionally requires you to implement 30 methods in your proxy. It's much, much simpler in Python because all the attributes a person tries to look up on your proxy can dynamically be dispatched through to lookups on the wrapped object. And then you can add an if statement if you want to do something special, which is the point of a proxy object. So some patterns become vastly more simple in Python because of this dynamic ability. Well, people got another idea. Instead of wrapping another object, what if we made something that appears to have every method you can think of? If you look up a name, it will say, ah, yes, I have a method of that name, and return to you a function. But it could instrument that method to record every time it's called and what arguments it's called with. You get an object that knows whatever methods you try to call will suddenly seem to exist and will be recorded. And this is now in the standard library and available to power your tests. A test, instead of actually letting you connect to the database or allocate a window in the operating system, can instead create a mock object, call your code, and see if the correct set of operations was done. Oh, that's so great, so powerful. What could be the problem? Mock, though widely used, encourages tests that in one sense are not really tests. The ideal is to have unit tests that get small collections of functions or classes, make calls to their facade, their outer layer of calls, and see how they behave. And then integration tests that really hook code together to see what it does together. I have seen code bases where the code is never actually hooked together like it would really work, where every single test is simply testing a piece of code against a mock. So the only guarantee you have is that it works against a fake object. But you never actually know until your customers try the code whether it really works. My complaint then is that, in fact, tests start to lose signal when mock becomes routine instead of a reluctant workaround. And I think our docs and blog posts too often focus on how to use mock. I feel like I've seen a dozen blog posts with that title, rather than also telling you when you should use mock and that it has downsides and dangers. A final built-in bit of dynamicness we like to take advantage of is called dunder call. The Python syntax, f, followed by some parens, is an operator named a call. F, in that syntax, is often a function or method, but it could be any other object instead. Any object can define that dunder method and opt in. And so, if you have a template class that only really does one thing useful, render, you give it some keyword arguments and the text gets filled in, well, programmers love brevity. And they think, well, I only have one real method. I don't have lots and lots of things the template can do that need to be distinguished from each other. Does the one method really need a real name? They look down at the bottom of the screen. Look at that. They're wasting 7 characters. Dot render. Well, that's the only thing a template in its right mind would do anyway. And so they make this pivot. They switch the verb that the template performs to dunder call so that now the template simply acts like a function. It takes some parameters and returns a string, and they are now happy and at peace with their code, having saved 7 characters every time the template is used. What's the problem? Readability. I realized this when I was debugging inside of a framework one day and saw a call like this. Get template args, close paren, open paren, close paren, open paren, close paren. What are those parentheses doing? I had no idea. It turns out, does anyone remember XHTML? Crazy, crazy times. This was back in the era of XHTML. The first pair of parens built an object graph that represented XML objects. The second pair of parens then flattened them to plain text. Could I tell that by reading the code? No. I'm sure it felt clever to give each of those objects a default verb with a dunder call method that didn't even have to have a name. But I am going to come out against that practice. I prefer to just burn some extra characters, have the line be a little longer, and know what the code is doing, know what operation is being performed. I, at all costs, avoid undercall in favor of real method names. But wait, I hear you call. You've thought of an exception. What if I'm working with an API that expects a plain callable? Then my class definitely needs a dundercall method. I have an excuse. If I am going to pass T to a framework and the framework says, pass me a callable, I have no choice. I'm going to have to be brief and add dundercall to my class. So the class needs a dundercall, right? My answer is no. No, it doesn't, because of a neat feature of Python called a bound method. The syntax t.method name does not have to be followed by a pair of parentheses triggering the method. It, by itself, performs an operation that JavaScript and other languages call bind, and that can be done, I believe, in C++ with a wrapper function. Dot by itself in Python goes ahead and does that operation that requires more work in other languages. T.render is a plain callable, acts just like a function, but when called, is a method on the particular object you use to the left of the dot. So even if your framework requires a callable, that doesn't mean that the method can't have a name. All right, those are a few observations of where I think people have gone a little too far in enjoying Python's object model and have maybe hurt their code's readability in the process. My third topic, getting serious now, Python's mutability. Mutability, the ability of things you've defined in your code to then start changing at runtime. If it sounds like a bad idea, it generally is. Let's look. For example, modules and classes in Python are mutable. You might have written them one way, but they can be changed later if someone is feeling unwise or adventuresome. If you import the default module string, and you don't like how limited the set of ASCII letters is, you can go change that constant to a new list of letters that you prefer. The language won't stop you. You'll be interested to see then how the rest of your application runs with this constant having been changed. In a class, you might set a class attribute value to 1, but someone can always come in later and change it to 2 because classes are mutable. In fact, not even methods are safe. You can come in later, overwrite a method with a new definition that you prefer, and the rest of the application will run with the new method in place instead. This, as you might guess, has over Python's history resulted in some predictable mayhem. Did I mention that programmers dislike repetition? Here's the sort of things they try. They love saying, I use the dry approach. Don't repeat yourself. And someone, I won't name them, was writing a web framework. And they noticed that if you pass an object representing the incoming web request to your views, your code has so much repetition. Request, 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 all the way from the top to the bottom of your application. Clearly, this needs to be fixed. They said, hey, Python global objects are mutable. Global object doesn't have to be a constant. It can be a live object whose attributes change. Let's eliminate the repetition. They decided to do this. Oh, let's not pass in the request as an argument. Oh, let's eliminate all that repetition and have it be a global object that you import. And then behind the scenes, when a web request comes in after importing your module, it can, for the new web request it's received, overwrite the attributes of the request object with the properties of the new web request, and then call your code that will see in that imported class instance the information that it needs. This, it turns out, I will argue, is a bad idea. Data, when you come back to debug something in the middle of the night later because a customer has run into a problem, data is now entering that function from two different directions. You can no longer read the argument list and have in your head all of the things that could change the function's behavior. Instead, live data is coming in from some import statements that could also affect the outcome of your view function. Tests are now going to have to mutate that global object before calling a view in order to completely control the decisions that it's making. Threads are going to have to overwrite that one request object. You're going to have to put a thread local in place so that different threads, all looking at the same global, can see a different set of attributes. And an async framework will now break your web framework unless you teach the async framework that each coroutine is going to need its own request object swapped into that global right before the code is called. And that's difficult if you've imported it and it needs to be injected into the views module. So there are a number of downsides to this. I just prefer the repetition so that I can see the data that my view is acting on. It's bad. But guess what? The situation can get even worse. There's another Python web framework that I won't mention that asked, why import request at all? If you have 10 different modules with views, you're having to repeat import request at the top of every one of them. It's maddening. Don't repeat yourself. And so that web framework loads your module full of views that reference a request that's never mentioned, and it doesn't matter because it gives your module a new global at runtime before calling any of your views. So request is magically there without boilerplate. Developers hate boilerplate, and this gets rid of it. The code is shorter. It also means that you now, unless you know the special rule, can't see where request comes from. It appears magically, and your IDE has no idea where it comes from. Say goodbye to tab completion. Say goodbye to right-clicking. Every time you mention request, little wavy red line underneath because VS Code can't see where it came from. It was done in the name of making code more brief. I'm not sure that it made it more readable or more useful. Global state. It's useful in emergencies, but shouldn't, we discovered, I would argue, be used routinely. What would an emergency be that might justify global state? I'll just briefly mention that gating is a big problem out in Silicon Valley, right? Deep inside of some code, you talk to a database. And now, someone comes to you and says, oh, we're starting a beta. It's private to just 3 of our customers, and we need them to connect to a different database. Well, good grief, by the time you're down that low in the code, you don't know you can't get at the current request, you don't know who the current user is, and the team hasn't been passed down there for you to make the decision. You could go through all of your code and start passing team everywhere, but the experiment ends in 4 weeks, or it's supposed to if someone remembers to back it out, and you don't feel like modifying lots of code that shouldn't have to know about the team just because we're doing an experiment for a customer at a low level. That is a situation where I've seen globals grudgingly used to good effect to get knowledge deep in a routine that shouldn't normally need to know it because we're doing an experiment, changing some behavior based on something the code wouldn't normally know. But except for situations like that, I try to avoid passing knowledge to routines through globals. I prefer instead to speak to them with arguments. Another use of code mutability is in code that's about other code, like tests. UnitTest.mock has another feature that I haven't mentioned yet. It is called patch. It manages mutability in a much more robust way than if you're running around trying to set values or install new methods on your own. Patch is used with a with statement, and while the indented code block beneath the with is running, c.method is going to be replaced by another callable that you provide. And patch is very, very careful whether the block of code gets killed with an exception or whether the block of code ends successfully. patch makes the guarantee that the original C-dot method is put back by the time the block ends, so you don't break all of the rest of your tests with a temporary maneuver. Patch lets you run with a class, a function, or a method briefly substituted for something else. Patch has therefore become the official mechanism for testing code that's coupled to side effects. Let's consider some simple code. You loop over some books. For each book, you want to fetch it, so you build a URL. For each URL at the very low level, you go and do an HTTP request to a server to fetch some information. Simple enough. Question: how much of that code on the previous slide can you test without triggering real HTTP? Start on the right. All right, we can't call download without real HTTP trying to run because it does a URL open. But notice that that's also true of the other routines. If you call fetch, it will call download, and a real HTTP request tries to go out on the network. If you call get books, it inevitably calls fetch, which inevitably calls download, which does real I/O. It turns out that not a single level of this hierarchy is callable without real I/O trying to take place. Are you going to need to run a small web server on localhost in order to test get books over there on the left? None of that code, in fact, can be tested without a web server up and running. The code succeeds in abstracting away the I/O. If you read the top level, you don't see any raw HTTP requests, but it fails to actually decouple it. Even though you can't see the web request being built if you're up at the top level, it still is an inevitable consequence of running that code. It's not decoupled from it. What is the solution to that if you want to be able to test get books? Okay, first, the real solution is to turn your whole application upside down. Look at my talks or other people's talks on the clean architecture, or in other communities it's called the hexagonal architecture, where you turn software upside down. I/O should happen up at the top level. The business logic that are in the subroutines shouldn't know where data is coming from or where it's going. That makes the lower levels easy to test. They're often pure functions. And then it's only when the top level is called that you're in danger of real I/O taking place. Okay, but what's a second best solution? Many of us are stuck in situations where we can't completely re-architecture right now, and things like the clean architecture are still emerging in the Java community, the C++ community, and Python. You might not yet know the clean architecture well enough to architect everything you normally code in that way. So if we want to keep the I/O on bottom, coupled to everything else, but be able to test, that's when we use patch. You go patch that I/O call, URL open, and now can call that top-level function get books, knowing that sample data from your patched version will be passed back to it in the test, rather than a real web request trying to take place. Unfortunately, not all programmers stop there. There is a worst case you can move to, where instead of patching the I/O, you think, oh, well, if patching is a good idea, let's not even have get books talk to fetch. Let's make a fake fetch routine so that all I'm doing is testing get books. Some people think that unit testing means each little thing needs its own tests, whereas in fact, unit tests means create a unit by choosing some edge of a smaller system and only test things from that edge. But it doesn't have to be as small as one class or function. The unit could be this whole little cascade of 3 functions. When people create units that are too small and are always using patch instead of letting get books really call fetch, then the same problem happens as with mock. You often get tests that don't actually test whether your application will work for your customers when the real functions are operating together, like testing objects with only mocks, testing functions with all their subroutines patched, falls short of being a real test. And you lose half the benefit of testing. Why? Because there's two reasons we should write tests. One, an automated alert when code is broken because it's better than your customers telling you. But two, noticing that, oh, good grief, I can't call getbooks without patching I/O is a hint that your architecture could improve. Writing tests and noticing, do you need patch and mock all the time, is pressure that helps you understand that your architecture needs to pivot towards more pure functions. If you're always patching and mocking the problem away, you lose that signal to improve architecture. So, Python is dynamic and allows us to change things at runtime. For tests, that's good. Heavily coupled code, if you've written it, you can move forward. It's still testable in Python thanks to patch. But there's a downside. The bad is that overuse of patch not only makes tests less meaningful, but ruins what the tests would teach us about our code's architecture. One last danger of mutability is import time side effects. Python modules are executed top to bottom at import time. Each module starts as a blank slate and runs its code sequentially. This is a surprise, and this is different than many compiled languages. Not only can a for loop, for example, run inside of a function, if you just unindent, you can have a for loop that runs and does I/O at import time. Now, why would you ever do dangerous or bad things at import time? It happens like this. 1, you start with your configuration, name and port of the database, living in the Python code. Number 2, on a dark night, you discover that that's an awful thing to do because a customer calls with an error, you roll back to yesterday's version, and because your configuration is in your code, you're also trying to use yesterday's name for the database server, which you had migrated last night, and you're now talking to the old data. So you switch. You now understand that config shouldn't live in your code. You switch to loading config from a file, but it's the middle of the night, and it's easiest just to do it from that top executable level of the module, because, opening a file, it's what Python does as it loads all your py files and compiles them, right? It's in the same spirit as what import is doing anyway at import time. Opening the little JSON file where we've now put the config feels so much like importing a Python module that we just go ahead and do it at the top level. So then later, it's another programmer that is at the helm when the config moves inside a database, and that code at the outside level of the module now tries to talk to Postgres to get the config, where you're keeping it centralized for everyone to read. And then the database port moves to Zookeeper. You can't even talk to Postgres until you've connected with Zookeeper. The result? A module that can't be imported or tested until Zookeeper and Postgres are both up, or you will get an error at import time, and it will fail. My advice is to never start down that road. Admit no import time side effects. At the moment you're tempted to add some executable code to the outside of the module, instead create a setup function that you call over as the first thing in your main routine. You want to keep your code importable without trying to talk to the database. Trust me. One last thought about this topic. You could do all kinds of things in a module, and I see people trying to do all kinds of things, specifically in the dunder-init.py. If you have a package, a directory called myPackage, import myPackage, in fact imports that dunder-init.py. If you say import myPackage.models, first the dunder-init.py is run, then models.py. If you say import myPackage.views, dunder-init.py is imported first and views. Dunder-init.py is thus an obstacle and a cost in the way of all of the other modules that you might want to import. Programmers keep putting code there, adding expense to any little thing you might want to import from the modules beneath it. And worse yet, some dunder-init.py files, for convenience, import all of the modules beneath them, thus ruining your ability to cherry-pick one thing you want. You now can't touch the package without waiting to load everything inside of it. My advice, which is not what everyone would say, is to keep dunder-init.py empty of code. Look at my Skyfield project. Skyfield's dunder-init.py has its doc string, so your IDE can tell you what Skyfield is, but it has no code. I do understand that my users don't want to have to import things manually from all dozen of my modules, so I have an API module that imports all the important classes, so you can say from Skyfield API import and the list of everything you want. I don't make people go ransack each of my modules separately for the classes they need, but it is possible to provide that centralized location where all your classes can be accessed without making dunder-init.py expensive. So consider pivoting to dunder-init.pys that are empty. All right. That ends my thoughts on some practices around immutability. I have one last topic to discuss. Object orientation. Indeed, the difficult and fraught topic of the subclass. I will give an example. There is an old module called threading. It has an object called a thread. As you might expect, you can get a function that defines a sequence of things to do. You can create a thread and start it running that function. But there's a second way to use thread. You also, as an alternative, can create a specialized subclass of it that has a run method that has all of the lines of code that you want to execute. It provides two different ways that you can provide thread with the code you want to run. Subclassing is a slightly awkward choice. You now have two new objects, a class and a method, instead of just one. Extra 4 spaces of indentation. You can't now test the task's code in isolation. You have to instantiate a thread first. It's a bit awkward, but it is an option. It is an illustration of a difference, very crucial, between composition and specialization, which I define as follows. Composition means putting simple things together. Specialization means making one thing more complicated. Crucial topics in software. A problem I have is that Python provides an extra temptation that some languages don't have towards using specialization as the way you construct software. It happens in something called the M times N problem. This is described, among other places, in the Gang of 4 book design patterns. You discover some of your programmers subclassing window because different operating systems work differently. Oh, but some of your other developers have been subclassing it to adapt it to different layout algorithms. Normally, this now means you're going to need as many subclasses as there are operating systems times different layout algorithms. The Gang of 4 say that you can get out of this M times N problem through something they call the bridge pattern. Have 2 separate class hierarchies, windows that are the low-level operations, and layouts which use those low-level operations. You then, at runtime, can get 2 class instances and at runtime compose them together, where one holds a reference to the other, where the layout algorithm has a reference to the window it should be using for drawing. Thus, an M times N problem, where you have a geometric number of classes you need to define, is reduced to an M plus N problem. You only need one OS window, one version of each layout, and you can mix and match them at runtime freely as needed. I will mention in passing that I think there is another pattern that in generality is even out beyond the bridge pattern. You can use data to couple code instead of behavior. The Gang of 4 don't spend much time on this idea. You can have a layout routine that, given the size, the metrics of the view, doesn't talk to any other code at all, but simply produces some data, a list of graphics objects that need to be drawn, that you can then pass to window.render without the 2 pieces of code knowing each other's interface at all, but instead only knowing the data classes. It's a little more work because you have to define the data classes. It takes more code, but it completely decouples the two pieces of code and even lets you jump in and do things like post-processing the graphics objects before the window sees them. Is there any advantage to coupling with nouns instead of with verbs, with methods? I like the insight of Fred Brooks. Writing in 1975, he famously said, "Show me your flowchart, your code, and conceal your tables, your data structures, and given just your code, I shall continue to be mystified. But show me your data structures, I won't usually need to see your code. It will be obvious." If Fred Brooks was right, coupling classes with data structures will be easier to understand than coupling them with behavior. And so this is called usually the pipeline pattern, where each element of software is able to run to completion producing data, and it's the top level of your code which hooks them together, which provides the relationship between them, instead of the classes needing to know that each other exist. So, the M by N problem, bad pattern, bridge is the gang of four solution, pipeline is if you move all the way to the code not knowing about each other at all. And now Python comes into the picture. And Python has a solution which doesn't even make you go all the way to the bridge pattern. Python provides a temptation to not even go all the way to that solution by doing something else, which are called mix-ins. Let's look at an early experiment that still lingers in the Python standard library. Now, I'm not criticizing the programmer of this because it was the 1990s, which were crazy times. We were just beginning to learn how a powerful object-oriented language should work. They wrote something called a socket server, a base class for writing services that receive incoming requests from the internet. These are the methods of base server. There's a lot of them. You might think, wow, that's a pretty big interface for users of this class to be calling. It turns out most of these methods are not the public interface. They're visible in the public interface, but you should never call them. The documentation specifies this. There are only 3 of these, which are in fact the external API that today we would move out into a facade class. But here, the 3 API calls that you use to start and stop the server are mixed in with all of these other methods that you're never supposed to touch, because it's when you call those public, those 3 main methods that they then call activate server, bind server, service actions. And then as a new request comes in, the asterisk, by the way, means that you're supposed to specialize those. You're invited when you subclass this to adjust those if you need to be particular to your service. You're not supposed to specialize handle request because it has a lot of complicated logic. If you want to customize it, there's 3 more methods that it calls that you can make more specific if your service needs to do special things to get the request, to verify that IP should be talking to you or not, and then to process it. Process request, if you don't override it, calls by default finish request, which is actually what handles the request. We finally actually do respond to the customer and send some data back. Because finish request could raise an exception or hit a timeout, process request runs it inside of an exception handler, and you can specialize subclass, handle error, or handle timeout if there are special cleanup actions that your server needs to do if a request dies in either of those particular ways. This single class is, in fact, several layers of behavior. You can see them right here. It took me 10 or 20 minutes of reading the docs to put this together and figure out where the layers were, but there are clear layers within this class that are interacting. Why are there so many behaviors on a single class? Well, largely because it was 1990, and back then the idea in object orientation was that the point of having classes was modeling. If you have managers and employees in your database, you want a manager class and an employee class. That was the idea they had back then. If we only have two nouns when we're doing low-level socket operations, you can have a listening socket or a connected socket, you necessarily will only have two classes, a base server and a handler, and you get everything having to do with a server and stick it on one class, and everything having to do with a request and put it on the other. If your training is to think of classes as structs for modeling the world, you'll create one class for each noun instead of for each interface or behavior, with the result that you'll generally have too few classes. You'll model patterns of behavior with dense graphs of method calls on the same object instead of clean, separate interfaces. You'll wind up with one big multi-story class instead of several sleek single-story classes that then cooperate together. The bridge pattern tries to get you to split things into layers, abstraction and implementation in separate class hierarchies. The S in the solid principle, if you follow that set of object-oriented guidelines, the single responsibility principle says classes should have only one reason to change. If you use two different reasons to specialize a class, then maybe it's two classes hiding inside of one. Alas, the base server has many reasons to change. So many different directions that this single class needs to be specialized. It really wants to be broken into separate layers, each of which has a single purpose, with the, again, a facade that provides only the public methods, and back behind it, clean interfaces you can specialize to specialize the network behavior and to specialize what the service does with the data it receives. Yes, 3 different classes at least are needed here to wrap a single actual resource. In the end, there really is only one listening socket, but to properly model its behavior, we need 3 classes, not 1. So, given the situation it's got itself into, how does the base server class survive, needing to be customized in different directions at once? Mix-ins. The fact that in Python, if you declare a class, it doesn't need to have any relationship to the class that's being combined with. Threading mix-in doesn't inherit from or adhere to or have an interface that relates to anything else. It's just a bare little class with one method. If when I create my service class, I list threading mix-in first in the list, its method will be preferred over base server's version of the method for processing the request. That is how the socket server survives its problem. You select the base class. You could have done it the other way, but you select the base class in this case according to the protocol you want on the network. Then you mix it with a mix-in that provides different concurrency models. That's how it lets you specialize in 2 directions at once without needing m times n different classes. Mix-ins let you extend a class in several directions at the same time without solving the actual problem, which is that the class is too complicated. So, that, I think, is in one way a strength, but in one way a weakness of Python, is that you can get around actually solving a problem that requires a real design pattern by stopping short of it and just using mix-ins with your overly complicated class instead. It's nearly 2020, and the reason I bring this up is that new Python books are still recommending mix-ins as the best-of-breed design pattern. I saw one the other day. There is a major Python web framework that thinks that mix-ins are the way to build views. This is still an active design pattern in the Python community that I think has better alternatives. I mean, poor architecture is going to happen despite our best efforts. So it's wonderful that Python does have powerful mechanisms for surviving it when it happens. But mix-ins too often, I think, become routine instead of an emergency survival mechanism. So In conclusion, looking back at all of these examples of the way that Python is very powerful, but that lets you work around things, I say that Python is a flexible and powerful language. It's so powerful that we often work around poor architecture without noticing it. A powerful language, then, by itself, is not enough. The ease and power of the Python language need to be combined with the experience of its community for healthy, long-term software projects. Thank you all for your attention. I'm Brandon Rhodes. We are out of time for questions, and I believe that coffee is now being served at our coffee break outside. I'll see any of you out there that want to follow up with questions or objections to my ideas. Thank you.
You can also choose this way out if you like.
a mówię coś.
Hello after the coffee break. We'll start soon. First of all, I would like to mention some rules. Please put your phone into the silent mode. Secondly, please don't leave the room while the lecture is ongoing. If you have a question, there most probably will be a section at the end of the lecture, and I would like you to queue here downstairs and wait for your turn to ask a question. Sleeping is allowed, but without snoring, please. And you can also rate the lectures on our CodeDive website. Our next speaker is Oleksii Pilkevych. I've met Oleksii a while ago on Nokia Toastmasters meetings, and at first he seems a little bit creepy, but to tell you the truth, he is a very nice guy, and he inspired me not to do certain things in life because I don't hate myself. Please welcome Oleksii Pilkevych with his speech, "Hate yourself, keep using Python 2." Hate yourself, keep using Python 2, Oleksii Pilkevych.
Hello? Okay. Huge thanks to Jarek for this introduction. I once did a talk about pornography on Wrocław Toastmasters, and it was very inspirational for Jarek, as he mentioned. This talk is kind of a big deal. I have a lot of friends here, both watching me on the stream and sitting right here. I have my parents. It's my father's birthday. And as for my mom, she doesn't really do programming, but if I say something stupid, she will just know somehow. So I have to be really careful. As for what you are currently observing on the screen, do you feel anxious? Do you feel fear when you are looking at it? Something terrible is going to happen in 1 month and 11 days. As you may have heard, it's the end of life for Python 2. According to a survey conducted by JetBrains, only 13% of people are still using Python 2. Those people on this sinking ship that is about to burn and explode. How many of those people are sitting here currently? About 13%. That's very accurate. I used to be on that sinking ship as well, but not anymore. Not because I migrated successfully, but because I changed my job. That's recommended as a fastest method for moving to better technologies. Right now I work in Perceptics, where we are trying to build a system for large-scale employee surveys. So what will happen if you do not upgrade in 1 month? According to Python documentation, if people find catastrophic security problems in Python 2, then most volunteers will not help fix them. Some of these problems will start on January 1st, other problems will grow over time. Now that sounds very, very gloomy, especially in comparison to what people in Python thought when they were writing Python 3. Turns out some developers hoped that the community would do what Python did and do one last release for Python 2 and then jump onto Python 3, which didn't happen, as you have probably noticed during the last 10 years. So while I no longer use Python 3, I still feel an obligation to talk about this issue while it's still popular somehow. This talk is not a tutorial on migrating to Python 3, but more of a desperate cry of my soul for my brothers and sisters who were left on that ship writing in Python 2. Maybe what I speak about today will help them find motivation, reasons, and tools for migrating to Python 3, and maybe it will help them convince their managers to do so. So as we see here, we have a very valid reason to migrate to Python 3. Or do we? Because there's a lot of legacy software in the world which still works. Banks are running in COBOL, and companies are still making a lot of money with legacy software. And Python 2 is not going to magically stop working on January 1st. It will still last for a long time. So what other reasons do we have? Maybe speed is another reason. Luckily, I found an article where somebody did benchmarking. And here we can see a graph. As you can see, Python 2 is really slow, and Python 3 is really fast. Or is it? Because if you look closely, those are some other Python distributions, and in fact, Python 3 is here. And as you can see, it's just a little bit faster than Python 2.7. And here they are benchmarking rendering HTML templates. But if we scroll down, they have a few more benchmarks where they do startup time. Turns out Python 2 is faster. On cryptography, also Python 2 is faster than on algorithms. Python 3 is faster. And if you scroll down, you notice that there's not much difference. Now, it would be a lie to say that Python 3 doesn't improve speed. As I read in an interview with Instagram developers, when they migrated Instagram to Python 3, they had 12% CPU savings and 30% memory savings. But it's still not this huge speed improvement like you get when you upgrade very old legacy systems. So maybe there are some awesome features, some vital differences that we need to know about to migrate to Python 3. Here is a list of links I found when I Googled Python 2 versus Python 3. And let's suppose I know nothing about Python 3. Maybe I'm a manager of a developer team, and I want to know whether it's worth to migrate to Python 3 or not. So we open the first article, and we see a user-friendly chart. Python 2 is legacy, and Python 3 is future. We kind of knew that. Old libraries built for Python 2 are not forward compatible. New libraries for Python 3 are not backward compatible. Makes sense. Now here we have ASCII in Python 2, and we have Unicode in Python 3. Well, luckily we have more characters to use. Maybe we can internationalize our application if we want to. But usually we do not, at least in my cases. We have improvements when it comes to division. Looks like Python 2 didn't know how to divide correctly. In fact, it did. You just had to use floating point numbers. So it's not like a super cool new feature. It's just a syntax change, which makes sense, but still is just a syntax change. And then you have the most vital part, the print function. What else do we have here? Well, spoiler alert, we don't have anything else. Oh, we have, why does Instagram and Facebook use Python 3? Because the ease of using Python and stuff like that, which we still had in Python 2. Maybe this article will help us. Okay, so here we have division. Oh, the print function. See, we have to use parentheses, and in Python 2 we could write something like this. Oh, division again. Unicode. X-range. Oh, this is also very important. In Python 2, you would write X-range, and in Python 3, to get the same thing, you have to write range. The rest of those features are similar. Here's another one. This one is actually one of my favorite ones. It has this section. Why should you use Python 3? Python 3 supports modern technologies like AI, machine learning, and data science. Never did, now supports. Supported by Python developers community. Too bad Python 2 was unsupported. Easier to learn, maybe a little bit, but not much. Offers libraries. Mixable with other languages. You probably get the point. I could do this all day. Here we have print function and division mixed. So what? Let's migrate. Let's devote a couple of months or more of our precious developers' time to migrate to this magic new language, which has support, libraries, and the new print function. Or not. I will digress a little bit before we jump into technical details, just to show you what mindset I would like to approach this with, and why the mindset we usually approach it with is kind of wrong, because it's the mindset we just witnessed earlier. Has anyone here read this book? 2 people, or yeah, 3, 4. Cool. This book is the most popular thing Mark Manson did, and while I'm not a very, very huge fan of this particular book, I'm a huge fan of his articles. And one of his recent articles is called "If Self-Discipline Feels Difficult, Then You're Doing It Wrong." And it might be helpful for us, because migrating to a new version of a language is a problem of discipline a little bit. We have to stop procrastinating and start doing it. So what Mark talks about it in this article is he starts with a story where in his young years he tried something called Uberman sleep schedule. The idea was that somebody in the Navy noticed that whenever you sleep, 80% of your resting comes from 20% of your sleep. And if you lead yourself to sleep deprivation, then you could go to sleep and your body would automatically trigger itself into this resting phase. And then you could wake up right after the resting phase and not waste your time sleeping. But in order to start reaping the benefits of the schedule, you had to condition yourself first for 2 weeks. So for 2 weeks, you would have to sleep for 20 minutes, then function for 4 hours, and then repeat that until you get used to it. And that what Mark tried to do, but he would always fail after 4 days. And the reason he would fail was, first, it didn't work. Second, he didn't get any immediate benefits from it. He would only get fatigue. So basically, the only thing he was running on was discipline and was willpower. And willpower is not enough for something like this. He sums it up really well in this sentence. You can will yourself to go to the gym if you don't feel like it for a few days, but unless the gym ends up feeling good in some way, you will eventually lose motivation, run out of willpower, and stop going. So first of all, we need a strong reason to do it, and second of all, we need to find something pleasurable in the process, otherwise we are going to fail. And I think this applies in software a little bit. The first time I noticed it was during this process. So what happened? I was in a project where we were developing Python libraries. At that moment, we didn't have a huge workload, and a new person was joining our team. So we thought, it's a great idea to write unit tests because we don't have any, and we have no idea how you write unit tests. So we had a lot of willpower and resources to cover our libraries with tests. So this was our strategy. If you've been here for the talk before, where Brandon was talking about bad Python practices, this is exactly what we used. The strategy was we find a random method, then we mock everything, every call to other method, other library. We assert which methods it calls, we assert what it returns, we have our test, and then we repeat it until all the code is covered. But unfortunately, the result was tests were basically repeating our library code. So whenever you had to do a change in the library, you would also have to change your test. Now you have 2 times more work when you are developing. And the funniest part was we had a library and another library that was using the first one. The first one was SSH, and the second one was some implementation for something. Both libraries were completely unit tested. But when the code was deployed, it didn't work because everything was mocked and they didn't integrate. The API of the SSH library changed. So not only did tests increase our workload, they also didn't notice bugs in places where they actually happened. So was there a better approach? I found a better approach. When I moved to another project, it had other challenges. We had a huge web application that would consist of many, many parts. And I got my first task, which looked like this. This application would monitor remote systems. And one such system had some kind of front end where you could do something as a user, and your task was to trigger a notification. And then our system that was monitoring it had to notice that notification, put it into the database, and display on its front end. So there you have the monitoring application, which runs in a Docker container. And by the way, there are very many systems that are monitored. So there are like 600 Docker containers and 600 monitored systems. And then all those Docker containers send data to another container which runs Django and has access to the database. And then another container with AngularJS would fetch data from the database and display it on our front end. So basically, the data had to travel through those 4 points. And as I was developing the code, I had to observe all 4 points simultaneously to see where a bug happens. So I literally had 3 monitors in front of me. On each monitor, I had one web page for the system front end, logs from the Docker container, logs from Django, our front end. I would click a button here, and then I would, in real time, observe what happens in the logs. Now, if you develop in such a way for a long time, it gets really, really annoying. You cannot even use one monitor for YouTube. So there had to be a better way. And there was a better way. A better way was just to mock the output to the monitored system, see if the monitor parses the data correctly, if it handles edge cases correctly, and if it sends data to Django. Then on the Django side, use Python Django extension and test whether the correct things are created in the database, and then use tests for our API and our front end to see if it renders correctly in the web browser, which we already had. Since I started using that approach, I could start developing features without even running the application itself. I would just write the tests, write the feature, then run the application once in the end, and it would usually work without any problems. So as you can see, I wasn't writing unit tests because I had to, or because I expected some benefit a year from now. I was getting benefits right away. And this was reducing my pain. And that's why it worked. Can we use it for Python 3? The answer is yes, we can. The problem is that because we read articles like I showed you before, we do not know what we are actually trading by not migrating to Python 3. We don't know that actually we are in huge pain because those articles do not mention it. This is reason number one. At first I was wondering if using the word suck is appropriate for such conference, but then I remembered what tracebacks look like in Python 2 and decided that it was actually fine. So here's what I'm talking about. You have some code. Say you bought a smart fridge. You can open it, and the only method it can execute is sing a song. For those of you who don't know, a context manager lets us create this object and clean up its resources after we exit this block. And in order to use this syntax, we have to implement enter and exit methods. So as you can see, this code is pretty harmless. It even says so. It imports some very harmless things. And actually, you can't see what this code is doing because it's all wrapped in this stuff that is imported. So let's say you run it with Python 2. Where am I? So here you have Python 2, and you run your code, and oh, there is an exception. Where does it come from? Let's look at the traceback. In fact, tracebacks are vital. They're supposed to help us. So they shouldn't look like they do in Java, but they should give us the points of what's happening line by line and where our exception happens. So we see that something happens when we sing a song here in this place. And we also see that there is a print statement here, and we don't see it in the traceback. But then we see the traceback leads us here. Typical cleanup function, which is not executed, right? Because let's think, we're doing this with statement, which is firing the enter method. Then somehow we executed sing a song. So this thing here was returned already. And then here we see this in the traceback. We're not getting the print statement. So it failed here. How could it get to this place? This is very strange. But after a little bit of debugging, we are going to enter the typical cleanup function. which is here, and we find the error. So apparently, somehow our code got to this place without executing this, and this exception fired. So let's comment it out. Run it again, and we see another exception, which leads us to sing a song, some harmless function. It didn't lead us here before. If we enter it, we see that it raises an exception. This problem happened before, but we didn't know about it. But what if we run it with Python 3? The traceback is a little bit longer, and surprise, surprise, actually readable. We try to sing a song, some harmless function happens, raises an exception. Then while we try to handle this exception, another exception happens. And by trying to handle this exception, I mean we go to the exit part of the context manager, because that is where you handle exceptions in the context manager. And while we're trying to do that, this function gives us another exception. Makes total sense. If you think that this is not a big deal, I once spent half an hour or an hour debugging something like this, because our application was more complex than this fridge, and in fact, I didn't even remember that the code I was debugging was inside of a context manager. I had no idea where the exceptions are coming from. And in fact, I had two of my coworkers ask me to help them debug an issue because they didn't understand what an exception meant. And instead of helping them, I just said, try running it on Python 3, and the problem was solved in 2 minutes. That might be an argument for managers. The most precious thing we have, developers' time, is being wasted because we are not using tools that are there for us. Another thing about exceptions is this. Raise your hand if you have seen this abomination in your code base. 1, 2, 3 people. Still some. I saw this in 2 projects. Does anybody know what this is supposed to do? I had no idea. It looks like this thing doesn't do anything at all. You have a custom exception that inherits from base exception and has a method raise with traceback. First question is, are there any exceptions in Python that are raised without tracebacks? And in fact, this syntax here makes no sense. When I was preparing this presentation, I didn't even bother to check what this does, because this is some code copied from Stack Overflow. It was in our repositories, and nobody knew why it was working or what it was doing. But after some research, you see this. Here is a problem. You are a good developer, and you want to catch low-level exceptions and raise your custom exceptions so that your user knows what went wrong. In this example, let's say you have some configuration that you want to remove. And you have to remove it from a dictionary and then remove it from the file system. And while you are doing that, those errors can happen. So you are catching those, and instead you are throwing your own error so that somebody on the top could intercept it. The only problem is when you run this code in Python 2, this is everything you see. And if this happens somewhere in production environment and you have to debug it from the logs, and you didn't expect it to happen, you have no idea why it happened. On the other hand, if you run it in Python 3, you see the traceback, which shows you that it failed on this stage and not on this stage. We have the exact same message. In fact, if we wanted to make it even more readable, we could use this syntax, which comes to us from Python 3. In this case, we see that this behavior was not accidental, but it was planned, because the message changes from during handling the above exception to the above exception was the direct cause of the following exception. Let's say we wanted to have something like this in Python 2. That's when our base error comes in. This is how we can run something like this in Python 2. We make our custom exception inherit the base error, and then instead of raising it normally, we raise it using this ugly syntax. But the problem is not just the ugly syntax, the problem is that it doesn't work like it does in Python 3. We see this delete cache configuration line, but the traceback is shorter and it is not as verbose and readable as it was in Python 3. And if we try to run it with Python 3, it actually doesn't work because the syntax is deprecated. So what if we want to run it in Python 3? We use compatibility modules. And our code starts to look like this. We import race with traceback from future, and then use a slightly less ugly syntax. But spoiler alert, in Python 2 we are still going to get this short traceback which doesn't give us as much information. So really, there is no escape, and even if you try, you write ugly code and reap only part of the benefits. And this was only mentioned in one article on the first page of Google search. I did. For me, this was one of the most vital reasons to migrate to Python 3. Now let's move on to inheritance. And with this one, I would like to do something crazy. How about migrating Python 3 code to Python 2? We have some simple code here. We have a car. This is Python 3. We have a car, and we have a race car, which inherits car and overrides start method to do something before it. So in pure Python 3, it looks something like this. The code is so clean, it doesn't even seem like anything is happening at all. We run it. Race car prepares nitro. Our car starts the engine. Everything works. Now let's try running it in Python 2. Okay. Super doesn't work. It doesn't work because in Python 2 by default we have old style classes and we have to inherit object. And you have to remember to do this all the time whenever you try to use inheritance. And if somebody thinks they don't have to do it in Python 2, but then somebody else has to reuse their code with actual inheritance, you have to write workarounds to make that class actually inherit object and start behaving like new style class and start using super. Let's try running it now. Super takes at least one argument. Okay, so that one argument is probably self. Oh, no, this argument must be type, not race car. Aha, so self is a race car, but here we need a type. And a race car is a type. Okay, so we can understand that probably this is what we need. And then we get another error. Eventually, we Google how to use super, or we use our IDE to help us, and we end up with something like this. After a few years of programming in Python 2, I still don't remember which arguments super accepts. Maybe somebody can empathize with me. This has always been filled out by the IDE for me. Now finally it started working. But let's say we wanted to extend this code. Let's say we want to have a flying race car. So we create another class that inherits race car, and here we are spreading wings. Looks good. This is our code. Let's run it. For some reason, we didn't spread our wings. Not only didn't we do it, but we also didn't notice that we didn't do it. And that's because we forgot to modify this. We had to put flying race car in here, and now it's working. For some reason, it's not. Aha. Yep. Yep, it's a little bit different. So it's not working in another way. We are spreading our wings, but we are running super for race car, which resolves to this. And so we are skipping the prepare this part, right? And we do not notice it. So once we modify this part, everything is working correctly, but we have to notice it. Now, what if we run it with Python 3? It still works in Python 3, but the code can be simpler. We do not need object. We do not need this stuff in super. And spoiler alert, because we do not need it, there is no chance an error like this happens in Python 3. If you want your customized super, you can still use it. But if you don't, your code is cleaner and a chance of errors is much smaller. This is another problem with Python 2. And in fact, with Python 3 as well, we have no idea what the hell str means. It's a type that is supposed to represent text. But it's not what it does. According to Python 2, str contains bytes, which probably are convertible to ASCII. So if you ask it, it will probably succeed, and you will probably have text. But if you want to be sure that you have text in Python 2, you are encouraged to use Unicode, which means you have to put a small U letter before your strings, or convert your strings to Unicode explicitly, which nobody does. In Python 3, you have Unicode by default in literals, and str represents bytes. No, str represents only strings in Python 3, and bytes represent bytes, like they are supposed to. But this creates tremendous issues during migrations. Here's why. This is a case we actually had in one of our projects because we were using a lot of SSH to interface with other systems. Here we have some code that creates an SSH client, connects to a remote server, lists files and directories, reads the data, searches it with a regex, and prints it on the screen. Working, because if it is not, it does. So we are getting our data. Now let's run it with Python 3. We get an exception. And this exception happens because we are trying to fire a regex search on bytes, not on strings. So apparently this has to be converted to a string in Python 3. Now it is going to work correctly. And this thing is not going to change anything in Python 2, because in Python 2 you're converting bytes to bytes. But in this case, our regex worked differently for some reason, and we have to understand why, because now we are getting a different output in Python 3. Now this is a larger discussion. A talk about Unicode would take far more than an hour. But the real danger here is that whenever we are trying to migrate code, we get this advice. Get some tools that check your syntax and put them into your CI, and you will know if your code is Python 3 compatible. That's what was happening in our project. We had tools that told us that our code is Python 3 compatible, which it wasn't, because those tools couldn't check which types we are receiving from SSH and how this stuff behaves. Another problem we faced was type checks. We were running tests in Robot Framework, and Robot Framework has this thing where whenever you pass arguments to functions, even if you type a number, it is converted to a string. It is interpreted as a string. So in Python, if you expect an integer, you have to first convert it to an integer. But what many people were doing is they were checking types. So let's say you want to know if something is a string in Python. And just by asking that simple question, you are already getting into a lot of trouble. Let's see if this code works. We want to print cod if it's a string, and print not a string if it's not a string. This is a string, this is not a string. Works well. But what if we pass Unicode? In fact, Unicode is a string, right? Turns out it is not, because in Python 2 it's another type. So we have to run something like this. And it works in Python too. But as you probably can see by this red line over here, it doesn't work in Python 3 because you do not have such type. You do not need Unicode. So in this case, you would want to check something like this. You would have to check if this is str and if this is bytes. And then it would work in Python 3. But spoiler alert, it doesn't work in Python 2 anymore. So we have to do something like this. We have to use future. And here an interesting thing happens. You import str from future, and now suddenly the built-in Python 2 str starts working differently. Instead of converting stuff to bytes, it now converts stuff to Unicode. And if you have a long script, which we did have, and we used a lot of stuff from future, I noticed that at a certain point, I had no idea whether the current str I am using is converting stuff to bytes or if it converts stuff to Unicode, which made our life even harder. And also, in this case, here is another issue. Let's say you want to document this variable. You want to tell other programmers which type is expected. And you say str, and you have no idea what it is. So suddenly, your interpreter in Python 3 tells you that this is not what it expects, which is the correct thing to do. It's actually helpful. But if you change your default interpreter in your IDE to Python 2, this is what you are getting. Expected str got Unicode, and PyCharm doesn't notice that we are importing str from future. So because of stuff like this, documenting Python code became much more difficult because nobody knows how strings look anymore. So what we ended up doing was we would just document it like this and make our IDE ignore it, just not to flood us with unnecessary warnings. This is a picture I found somewhere on the internet, which actually explains what decode and encode methods do, which, to be fair, in our code base, we would use randomly just to make the bad words disappear from the screen. Another issue is imports work in Python 2 in a very unpredictable manner. And even after a few years of writing heavily in Python, I still have problems with imports every couple of months because I forget how they work and what they import. Here is the problem with Python 2. Let's say you have a project that looks like this. You have a main script which imports a module which imports script from this module. This is the script it imports. This script, on the other hand, imports common. The question is, which common does it import? This one or this one? If you import the global common, which is in the root directory, this is what you are going to get on the screen, imported global common. If you import the local one, you are going to get imported local common. So which one are you going to get? The answer is, it depends. If you run this with Python 2, you are going to import the local module. Which means this one. But if you run it with Python 3, you're going to import the global one. Question is, which one do you want to import? Let's say I'm on Python 3, and I decide that actually here I wanted to import this module. The solution is simple. I just write from dot import common, which means import common from this local package in here. And now suddenly, now I'm importing local module. What can I do in Python 2? Because in Python 2, with this code, I'm getting the same local module. And without this code, I'm getting the local module as I did before. What if I want to import the global one? The answer is you have to use from future import, absolute import. Because by default, Python 2 cannot do something like this. Now this thing I'm especially proud of. Probably you are not going to experience this case yourself. It was a huge coincidence that we experienced it. I was conducting a TDD workshop based on training materials by Grzegorz Latuszek, who performed on Code Dive a year ago. And this was the idea. We had a spaceship. We wanted to show people that writing tests before writing code actually helps you in the long run. So this is the code. We have a spaceship that receives a direction in it. Directions are labeled as north, south, east, or west. If we want to turn left, it changes its direction. If we want to turn right, it also changes its direction. Then we had tests. Those tests were written in PyTest. We have a fixture which returns us an instance of a spaceship that is directed north. Then we test if it turns left correctly. We test if it turns right correctly. First of all, we enter a direction, then we turn left, then we check if the direction looks as expected. For example, if the ship is pointed north, once it turns left, it has to be pointed west. And that's what all of this code does. Now, what we did after that was we decided, what if we want to change the implementation but preserve the API? The idea was we wanted to optimize our turn left and turn right methods, and we wanted the spaceship to operate on actual angles and not on dictionary mappings. But in those tests and in the non-existent supposed client code, we were using directions. We were setting a direction, we were checking a direction. And we wanted to show the power of Python properties, because we can conceal the implementation behind the property. So here we have a mapping of directions to angles and angles to directions. And here we are concealing our implementation and reaping the benefits of turning using angles. The problem was, the whole idea of this exercise was to observe other people writing code and just guiding them. So I had someone from our training sitting there rewriting this code to this code. And this person forgot to write the setter. He only wrote this property. So the idea is that what happens now, whenever we try to set the direction in our test, in this place, something should happen, because we do not have a setter. It shouldn't succeed. Let's see what our tests look like. In the original spaceship, we could run PyTest with Python 2, and our tests would pass. But in the new spaceship, we would run those same tests, and they would fail while comparing directions. Why are they comparing directions? We cannot set directions, we do not have setters. And that was the problem, because I expected to get another exception. In fact, I expected to get an exception that I would get if I ran this code with Python 3. Can't set attribute, because you don't have a setter. And once you have this setter, tests work in Python 3, but they do not work in Python 2. And why is that? Well, that's because apparently there is some bug in PyTest in Python 2. And when you have this fixture and you assign to direction, you do not actually execute the setter, you overwrite the attribute. And this is something we found accidentally because another person on the workshop said that everything is working correctly. Turned out that that guy was just running his code with Python 3. Now, there are many more features which are kind of cute in Python 3 and should boost your motivations to migrate. Those features are type annotations. Instead of writing something like this, flooding your code with useless doc strings, you can do something like this and have type hints. Instead of writing classes like this, you can write data classes. You wouldn't have to implement methods like equality and hashing. Instead of flooding your code with arguments for format, you can use f strings and have a very readable and compact code. You can use keyword-only arguments. This is something crucial. If you want to forbid your users from entering arguments positionally, you can force them to enter arguments only by their names, so that this line would fail only if you put a star here. And now you magically forced all your users to write code that is readable. And also, if, for example, in this case, you want to add database username and database password, which are optional, you can do something like this. Your code is not going to fail. This line still works. Now, I could talk about features all day, but the question is, how do we actually migrate? This is how we migrate. It's not actually a huge rocket science. If you Google it, you will have a lot of tips and tricks. You have packages from Future that help you convert your code automatically or use some compatibility features to make the transition smoother. But the thing is, it depends on your project. Question to Jarek, do we have 5 more minutes?
Yes, we do.
Cool. So I had 2 cases. The first one was the project with libraries. The second one was the project with the web application. Here is a little diagram of how it worked with the libraries. This is what our system looked like. So we had a huge central server that had all the libraries installed, and it had Python 2 interpreter. The testers were writing tests in Robot Framework, and they were sending those tests to the server, which was executing them. The problem was, we wanted to migrate from Python 2 to Python 3. The good part was that most of those libraries were really trivial. They were only using SSH, a little bit of database, HTTP requests, SOAP requests sometimes. Migrating it to Python 3 wouldn't take a lot of time. And in fact, there was a team that started this huge migration process. And they contacted all developers and told us, please make sure your code is Python 3 compatible. And we thought, yay, we're getting to Python 3. So we made our code Python 3 compatible. We faced all the pain regarding Unicode, which I showed you earlier, but the migration wasn't happening. We were asking the guys, how's it going? And they were saying, well, it's going slowly because other teams are not migrating for some reason. In fact, those testers who are sending the tests to the server can attach little Python scripts to those tests. and we had no idea how those scripts were written because they weren't even checked by CI. So at this point, this migration became almost impossible, and in a month or two, turned out our libraries were not actually Python 3 compatible because we stopped checking compatibility. This project is still in Python 2, and I have no idea how it is possible for it to migrate to Python 3 unless all the teams cooperate. This was case 2, the application for monitoring remote systems. The good part about it was each application was separated into its own Docker container, so it didn't really depend on other applications, and you had complete control over your interpreter. The problem was the stack was a lot more complicated. We were using Django, Django channels, Twisted, Django REST framework, and more. So we had to adapt. But at least we could start taking it bit by bit. And what I actually did was I migrated an application to Python 3. The task of that application was managing Docker containers. So it would receive requests via WebSockets, and it would have to either start a container or remove a container. And also it would have to notice whether it is in Docker Swarm mode. If it was, it would create and remove services, not containers. So the good part about this application is it had only a few use cases. So you could easily cover it with tests. I added tests that check whether a container is created, whether it is updated, whether it is deleted. Same things for services, assertion whether statuses are sent to backend. The only challenge was I had to test it on real containers and services, not mocks, because I had no guarantee what this stuff behaves like in Python 3. Once I did it, migration to Python 3 took 10 minutes. Here are some other lessons. Since we are running out of time, I encourage you to Google how Pinterest and Instagram migrated their code bases to Python 3. If you look at those slides, they're really nothing very revolutionary in this case. Upgrade dependencies, make your code compatible, test, migrate production to Python 3, remove rubbish for Python 2. They also had some interesting cases with Unicode, which there are plenty of. This is how you would summarize tips from Pinterest. Using Futurize, the interesting thing was that they were running an automatic tool for fixing their code, but they would run it one fix at a time. So for example, they would migrate all their syntax for print functions, and then they would commit it, and you would have a diff for that single fix. So you didn't have huge diffs where you do not know what's going on. Of course, they had unit tests, and they had to separate them in a sensible manner because a lot of code is Python 3 incompatible, and their test wouldn't run if they had it all coupled. In case of Instagram, they also used the approach with small diffs. In fact, as they say in this talk on YouTube, which I encourage you to watch, they didn't use branches. They would throw everything into master. Of course, those commits they were throwing into masters had to be checked really well. But the good part was they didn't create a separate branch for Python 3 migration, and therefore they didn't have to deal with merge conflicts later on. They would continuously upgrade it to Python 3. They forbid incompatible dependencies in their CI. They also ran automatic tools for code migration one fix at a time. They had unit tests, and they had gradual rollouts. Here are some slides stolen from Instagram. First of all, they had a timeline, so they actually had a plan to succeed, not some vague idea of a migration. And looking at Jarek, I see that we probably have to finish, right? Okay, so I strongly encourage you to see this talk yourself. It's available on YouTube. This presentation is also going to be available, as well as a link to my GitHub with the examples I was showing and more. To summarize, if you want to migrate to Python 3, have a reason, have tests, and have fun, because willpower is not going to do it. Thank you.
Thank you, Oleksii, for your speech. I encourage you to go outside and grab a coffee. We don't have any time for questions, so if you have any questions to Oleksii, please approach him here or off stage. Thank you.
Dzięki.
Test. Can you?
Hello after the coffee break. Please take your seats. I hope that another coffee will kick in just in time for this lecture, for you to be fully awake. Our next speaker is Christian Barra, who is a problem solver, hungry to discover new things and dive deeper, whether related to his professional or personal life. Christian has a quite rich Twitter, so I encourage you to have a look after this lecture. Please give a big round of applause for Christian Barra with his speech, "Software is feeding the world."
Hi, thank you. Thank you for the great introduction. My name is Christian, and today I want to talk about why I think that software is feeding the world. So, first of all, do you know this guy? Have you ever seen this guy before? Raise your hand if yes. No, no one. Okay. So this guy is Mark Andreessen, is a venture capitalist, and he's one of the co-author of Mosaic. It's the first browser, and is also a co-founder. Was the co-founder of Netscape. And a couple of years ago, he wrote a really interesting article on the Wall Street Journal with the title "Why Software is Eating the World." This is a copy of the article. You can check it online. Actually, it's pretty interesting. I think it was written like in 2007. And the article tried to explain why software is reshaping our life and changing the world at the same time. But today, I would like to take that sentence and I would like to rephrase it a bit. So, can software feed the world? And before answering this question, I would like to ask you another one, which is, why should we bother? Does anyone know the world population today? Any number? 5 billion? 7. It's 7.7. And by 2050, it's going to be 9.8 billion. And it's a huge number, actually. And that number will put a lot of pressure on our ecosystem. And to feed world population by 2050, we need to increase crops production by between 25 and 70%, which it's a huge increase in production. But that's not the only big change that we will see in the next 30 years. What about people living in urban areas? So today, this 68%, it's about 53. So in the next 30 years, there will be a big increases in people living in urban areas, which means having cities with 20 millions, 30 millions. And that also means that the majority of the world population, more than 4 billion, will live in cities, will live in big cities. And if you think about this for a second, if the majority of the consumers are like in big cities, how do you move the food around? Can we keep producing food far, far away from the consumer? So we have a couple of problems coming from this growth of population. The first thing is that we need to avoid hunger. We also want to make cities more sustainable. We cannot increase like croplands. That's the size is limited. And sadly, because the majority of the Earth's surface is made by water, we cannot terraform the sea. And like these are not just problems, are also constraints. Like for example, increasing croplands, like I said, it's not possible because it's going to be counterproductive. Like we cannot keep destroying forest to make more land for us. And another thing is that we need to consider is that the world of like developing countries will change, will become closer to our habits. And that means that they will start consuming food in a much more different way, which is at the end closer to our daily way of consuming food. So what should we do? Like, we have a big list of problems. These, to be honest, they are pretty big. They're like different solutions. Like, they keep talking about this thing for the last 30 years. Like many solutions have been proposed, but at the end we can summarize them in 3 broad categories. So the first one is to change our diet, which means migrating from heavy red meat-based diet to a more sustainable one. That's the first step. It's something which was also suggested by the last IPCC panel. I mean, the document, the review from the International Panel for Climate Change. And these are the outcome of reducing croplands to feed animals. Another thing which is really important is reducing waste. I don't know if you know, but between 30 and 50% of the food which is produced every year, it gets wasted, like during the path, which is really a lot. Like if we produce like 3 tomatoes, just 2 or maybe 1 of them reach our plates. And the last point is to use technology. And when I say technology, I mean like using technology to increase, for example, crops yield, so to get more from our lands, or to rethink about agriculture. And I want to show you a video, if it works. Yes. So I work as a senior software engineer and tech lead for a company based in Berlin, and the company is called Infarm. And what we do is vertical farming at scale. So what you see here, these black boxes, are not fridges, are not like just storage boxes, they are farms. And what we do is farming as a service. So we don't provide farms, we provide herbs or crops. And what you see here is a picture from Edeka. Edeka is the largest German retailer. And just to give you a number for Edeka in Germany, we produce about 120K plants each month, just for Germany and just for Edeka. What you see here is a farm. It's something that we developed like internally. It's like, it was, I think, like a 3 years old project. And we can grow currently inside each of this farm something like 35 different type of crops. Can be basil, it can be pak choi, it's pretty diverse. And we grow the food locally, like closer to the consumers, like inside the cities. And for us, a farm is a technological platform to grow food at scale, which means that we have this concept of farm. We can deploy the farm wherever we want. Can be USA, can be Japan, can be Warsaw. And we just need water, energy, and we can just grow things inside. And to give you more numbers and context, we operate right now something like 500 farms all across the globe. And the goal is to reach 1,500 in the next 4 months. And like marketing-wise, we use like 2 words which are like 100% local. It's next to your neighborhood. And because of the technique that we use, we can have like 0 pesticides. So when you buy something from there, you don't have to wash the plants because they are clean. So, but because this is like a tech conference, let's talk about code and hardware. So this is a mass production farm. It's the core of our production pipeline. It's bigger than the black one that you saw before, and it's what we have in what we call like hubs. So if you come to Berlin, we have a hub in Tempelhof. We are right now also active in Seattle in USA, and we have the same thing. So what we are using as a technique is called hydroponic. So we don't have soil inside the farm, but we have only water with the nutrients. And from the seeding phase to the harvest phase, it takes about 4 weeks. So in 4 weeks, we can pretty much grow whatever we want. And as you can probably imagine, like a farm is a really complex living system. I mean, we are growing living things inside. but from a technical perspective, is a complex IoT device. And as a complex IoT device, we want to operate the farm. We also want to control the farm, but also we want to monitor the farm. And what can we control inside the farm? Well, we have different sensors and actuators. We can control water, we can control air, lights, as you've seen from the video before. We also have pH control and the nutrients level. And because we are operating more than 500 farms, we need in different multiple locations, we need to do this at scale with different time zones, which is not really straightforward. And to accomplish all these things, we are using different pieces of technology. We use Python, mainly for the speed of iteration, because we want to deliver like features in weeks and not in months, and also because he has a really great ecosystem of libraries. But we also use C++ and also C, especially for the IoT part. We have some really strong hardware constraints. And like just to give you some number, we have like less than 100 kilobytes of RAM. So we really need to be wise with about the number of variables that we use when we want to put something new inside the IoT devices. And we are also using Go, especially for the new generation of farms. So as a software team inside InFarm, we have 4 areas of focus. We have what we call operations, farm control, monitoring and alerting, and crops quality. So operations are all the activities related to operating a farm. So we have this role of a grower, and as a grower, you go there, you clean the farm, you seed, like you put things, you put like seedlings inside the farms, you harvest things from the farms, and these are all activities that we provide and we schedule using a software. And then we have farm control, which is controlling the farms. Like I said, we can control different things inside a farm. We have different parameters, like water, lights, and a collection of all these parameters is what we call a recipe. So what we can do using the farm control is to send recipe, so a configuration, to the farm controller, the microcontroller inside the farm, which then apply all these parameters, like I want this water level for the next 4 hours and all these things. And then because we have such a complex collection of IoT devices, something that we need to do is also to monitor all of these devices and also alert people, because we have ops team in all the cities where we have like farms and hubs. So we collect a lot of data, which are like metrics, values, and statuses coming from the farms. Just to give you an example, if you don't have water inside a farm, that's a big problem because your plants are going to die. Is the pH too high? That's also a big problem because you're gonna burn the plants. So monitoring and alerting is fundamental because it helps operation doing a great job. And the last pillar is crops quality, which is about using data science and artificial intelligence to increase crops quality and also to fight and prevent diseases, or just to improve taste of our plants. So I took this screenshot like yesterday, and this is just one of our data pipelines. So we receive on a daily basis about 3 million events, and in a month they are about 90 million. And these are just events and data coming from the IoT part. But to be honest, to get here, it took like quite a long time, especially on a quality perspective. When we started, the company was completely different. Like at the beginning, like currently we are focusing mainly on B2B, so we work with big grocery chains. But before, like when the founders started, they were thinking more about B2C. Like, okay, I want everyone living in Berlin, I want them to be able to grow plants inside their apartments, inside their flats. But after a couple of months, they realized that that was like a good fit for the business, and they decided to switch. But they built the software for something completely different. So as the business changed, also the software has to follow the same path. So at the beginning, we had a really small team. We had a really big Flask application, which was like a big monolith. everything, all the pillars were operated inside the same application. So operation, farm control, monitoring and alerting, they were all inside inside the farm. Inside the Flask application. And we had, and we still have, a lot of background tasks and jobs. And a couple of months ago, we started like facing issues, especially when we grow like from just a couple of farms to hundreds, especially scalability issues. Another thing that we started to realize quite soon was that the software was hard to be maintained because we were relying on too many external dependencies. So there were like many libraries to do the things that we needed, but it was really hard to, as you grow your business, as you change your scope, it was really hard to keep like the same quality level. Another thing is leaky abstraction. So because we really didn't know what we wanted to do at the beginning, we were just abstracting things to be able to scale in the future. But we were really missing, the core part of our business. And for that, it took like quite a long time. So you say, now we are really sure about what we want from the application. Like all these side cases are not important anymore. And another thing which is quite specific to Python is what I call normalize. So all the business domain, all the business logic was partially inside the ORM, which is fine. But at the end, it's really hard to change your application and to evolve your application. And that's what I call like our technical debt at Team Farm, especially for the software team. These are things we are working on and we are trying to improve every day. And another thing, and that's more on the upside, is that like when I joined the company, more or less like 1 year ago, we weren't using containers at all. So it was really hard to have reproducibility between like different devs. What worked on my computer probably wasn't working on your computer. We lack a lot of flexibility from one of our main cloud provider, which was Heroku. As we started to grow, we saw that many of the things that we wanted to do were really hard to do. And we had this incredible problem with metrics and logs. So it was extremely hard because they didn't matter before to really understand what was happening inside our applications. And last but not least, because we wanted to try, or because they wanted to try all the things available on the market, we decided to split our infrastructure across 4 different providers, which was pretty hard because then we started to see like how do we connect all these things together. We are running on AWS, we are running on GCP, we are running on DigitalOcean, we are running on Heroku. So our platform was scattered across different providers. And this is also connected to the normalized part and to the fact that we had this big monolith application. We were doing everything inside the application. So that means also ingesting all this data coming from the IoT devices. And that was killing our performances. So we decided to evolve, and we decided to evolve across these 4 different levels. So we decided to consolidate our infrastructure. We decided also to evolve our architecture. We decided to become more cloud native, and I will tell you more about this later. And we decided also to introduce a concept about observability. So the first thing is that we decided to deprecate all the cloud providers apart from GCP. So we decided to, okay, we're gonna move all our application workloads, servers, databases inside GCP. So everything that before was running inside, I don't know, AWS as a cloud, as a Lambda function will become a cloud function inside GCP. Another thing that we decided to, not just to say like, yeah, it's pretty nice to, yes, let's pay technical debt, but we decided to put time on this. So we decided to groom like our technical debt and to put like a serious effort into dealing with all these things. Why it's so important? Because we started to realize that many people were saying, I cannot build this feature, I cannot change this because I don't understand the software, or because it will take I don't know, weeks or months just to, make this small change. And that was really slowing down the company and the business. Another important thing, especially for dynamic languages, is using linters. It really speeds up the deployment, and you feel safer, and also you avoid having tricky conversation about the style of your code and things like that, which are pretty boring. And we decided to reflect on these two concepts, like build versus buy and manage versus managed. Especially if you're in a small team in a fast-growing company like Infarm, we received 100 million of funding during the last summer, and so we have a lot of money to spend. But at the same time, we need to deliver a lot, in a really small amount of time. It's really hard, to keep on with everything when you have a lot of requirements coming up from business. So we decided to avoid building new stuff if they are not really a core part of the business, and the same is about unmanaged and managed. So just to move on all the levels, on the architecture side, we decided to move on a more service-oriented architecture. We decided to start splitting our monolith into microservices or services. And this will not just help with, having a more decoupled system, but also it will make clearer what are the separation between and the boundaries between your business unit. And another thing that really helped was to move data ingestion from, a Python application to Cloud Functions. Now you have, scalability is not an issue anymore, and you can scale as your cloud provider will give you the opportunity to scale. Another thing, and is connected to the data ingestion, is that each farm has a Grafana dashboard. So every time that we change something on a farm, we had a new sensor, or just because we are adding a new farm to a grocery shop or to an app in a city, that farm gets a dashboard, a Grafana dashboard with all the data. And the operation team can just go there and see all the data related to farm in a sort of super automated fashion way. So you don't have to do something as soon as we receive new events coming from a new ID from an IoT device, we create a new dashboard. And there's not the dashboard, but you also get the alerts and all these things. So another level where we decided to work on was cloud native, and the first action that we took was to containerize everything. Now everything that we do is based on containers, on Docker containers. Every time that you open a pull request, we have a CI/CD pipeline, and what you get is a container and all the tests, all the QA related to that application, or to I don't know, just even about the deployment is a Docker container, is a Docker image. And to be honest, the next generation of farms, we will have containers running inside the IoT device. Another step that we decided to take was to introduce infrastructure as code. We are using Terraform at Infarm. It's pretty neat. It's basically you can destroy and recreate your infrastructure in a couple of seconds with just 2 commands. Like I said, each image is a Docker image, which is also pretty handful, especially if you have problems. You can just download your Docker image and you can test it locally. And we decided to migrate to GCP, and we decided to run all our containers inside Kubernetes. So we're using GKE, which is the managed solution by Google. And the only thing that we need to decide is the number of nodes that we want to run, and they will take care of managing the masters and all the boring things about Kubernetes. The other level, which is really important, is observability. When you're operating distributed systems at scale, it's pretty annoying to do debugging and try to understand your system, because you have these calls and they're across multiple applications, multiple things, maybe also multiple cloud providers. So something that we are still working on, and we are trying to put more effort, to be honest, is to, first of all, we decided to adopt structured logs. So now you have like contextual information when you log something. Who was the user? What was the origin of the request and all these things. Another thing is, it might look like naive, but we were missing metrics. Like we had metrics coming from the cloud provider, Heroku, but they didn't provide like a lot of information related to what we were doing and what we were not doing properly. So things like the number of 5x requests that your system is doing, or why is this error coming, or is this error like coming every day at the same time? It was almost impossible to answer these questions. And to integrate all these things, because we decided to migrate to GCP, we decided to put an effort on Stackdriver, which is the managed solution by GCP. And to be honest, I think that we put effort on logs and metrics a bit too late. Now we're really firefighting with all these things because we are like in a growing phase of our company where we are deploying more farms than releases in our software. So I really feel we started to, being like more concerned about the quality of our software, but also the quality of our infrastructure. And the implementation by GCP, it's really, really handy. Like, especially if you're using GKey, which is the Kubernetes by Google, you don't have to configure something. So you get logs and metrics for free. The integration is pretty neat, and then you can extend them if you really want. And if we take like a step forward and we think about the future, these are the things that we see. So we want to have a more service-oriented architecture, like I said, especially because we want to open our infrastructure to not just to new provider, but also to users, because we are collecting a lot of data, and something that we can really do with vertical farming, but in general with indoor farming, is running a lot of experiments. So in 4 weeks, we can see what works and what doesn't, and we can really find the best parameters to, grow your food. Also, just as a farmer, like what is the quantity of nutrients that you really need to provide them? Another thing that also we started to see, and we think that microservices will help, is to decouple teams. Sure, then you will have problems in defining like the proper boundaries and the proper interfaces between different teams and how their software will communicate with each other. But we moved from like just a couple of teams, like 4, to 10 teams, and now they have different requirements, different KPIs. So it's really hard to keep everything together, to keep everything on track. So, and they want to deliver in the same quarter probably. So something that we are experimenting, and we see it works more or less pretty well, although there is still work to be done, is to separate all the teams, define, okay, if you need to use my API, this is the interface, I'm not going to break it, and in case I need to do some changes, I will do like a pull request, and I will just ping you. And the last thing is you could like focus on data, because it's extremely important. Like you can really play with the system, but you need to be aware of what is happening like inside. Like you can tweak all the parameters and you can get like amazing basil or amazing tomato. But you really need to control, what is the right amount of light that you need to provide to the plants? What is the right amount of water that you need to provide all to the plants, and all these things? And like I said before, sorry, one of the things that we plan to do is to expand our platform. Think about like open data platform for farmers. So the future is not just that. Like currently we're working on the 2nd generation of farm, which is completely different from the picture that you see here. And there are like 2 main drivers. The one is fully automated farms, which means that we really want to reduce like labor work. And not just because it's expensive and you have a lot of people operating the farms, but also because people are a driver of diseases. So every time that you open a farm, you're putting something inside, and probably it's not good. So we have diseases coming from people, and it's really hard to fight them because we are not using pesticides. So everything that it seems like easy or like it's not a problem anymore in traditional agriculture, for us is like a big deal. And another thing is, you maybe have Alexa, and you can call Alexa and say, I want, I don't know, like 20 grams of basil the next week. And that's something that you can do with an automated farm, because we can produce on demand. And another thing is that we can produce all over the year. So the concept of season for us doesn't make any sense, because we can produce the same type of crops with the same quality, with the same nutrients in December or in July. It doesn't change much for us. And another thing, especially for the second generation of farm, is to change the microcontroller. So currently we're using IoT provider, which is called Particle, which provides a really nice integration with the device and the API, but you're really limited about the things that you can do there. So you cannot run containers there. You have, I don't know, just a couple of kilobytes of memory, and that's everything you can do. So the next phase of FinFarm is really about edge computing with artificial intelligence on the top. So the plan is to have like really computers running inside the farms, and there we will be able to run containers, run more software with like more complex algorithm and all these things. And these two things are really important because they will shape and change like the industry and the concept of vertical farms. Like, to be honest, like there are a couple of problems related to this system, which is we can use 90% less of water, but we use 10 times more energy compared to traditional agriculture. And we need to become much more efficient. And again, connected to edge computing, especially about the topic of artificial intelligence, what is really important is to be flexible. Like we have like some actuators and data, and currently when you want to grow something inside, we have this collection of parameter of configuration, which is called a recipe. And they're basically are coded. So you have a scientist, you have a biologist coming there every day and saying, okay, here I want to grow basil and something else. What is the best recipe? But maybe the best recipe in Wrocław is not the best recipe in Berlin. But right now, the only way to apply these changes is to go like on the website and apply them manually. What we want to do in the future, especially because we have farms all across the globe, is to put this freedom, this flexibility inside the farm. So what is the right quantity of light? It will be up to the farm to decide whether 10% or 90% is the right quantity. And to do this, you need to push a lot of competition closer to the farms. So, thank you. I hope you enjoyed the talk. And something that I really wanted to share is the power of technology when it's connected to the real world. Something that I didn't share, but that happens like quite often, like at least in the previous month, is that when you deploy like a bug in production, what you get, I mean, you kill the plants. But at the same time, you really see the effort and the outcomes of your job every day. Thank you.
If you have any questions, it's now good time to come here and could you please come here? If we have more questions, please queue up in front of me.
Hi, I was curious about these evaluation of the quality of the crop. How does it work? If you could just highlight roughly how it evaluates automatically whether the basil is better or worse.
Sure. So there are like a couple of things. Some of them are quantitative, and some of them are qualitative. So we have like people tasting the plants, but also we have people on the qualitative side, on the quantitative side, taking pictures, because for example, for the grocery chains, they want to have a proper site, and a proper width. Another thing is that you can do like X-ray, and you can analyze like the nutrients inside the plants. So that's what we do right now. And you can do like other things related to the color, for example, and to the quantity of chlorophyll inside. So there are like different parameters you can check.
I would like to ask you to stay seated for a while until the question part is over. Thank you.
Hi, great presentation.
Thank you.
I really like the idea. I have the question because we all want to reduce the carbon emission, and we know that energy usage is not constant. So you have the peak, and you have also energy which is wasted. For example, nuclear power plant is producing constant energy, but you don't need all this energy all the time. Do you think about using that, so give more light to what you are doing when the energy is cheaper, and do not use the light when it's not necessary, to give it more environment friendly?
So what I can tell you is that during the last weeks, we had a lot of awareness inside the company about energy consumption. That's like the main driver for the next months to reduce energy consumption. So you can play with different things. Like especially in Germany, we are just you can buy 100% green energy. But that's just one of the things that you can do. Another thing, especially when we work like inside apps, is to recover energy. Because yes, we can produce all over the year, but producing in Berlin or producing in the south of Germany is different, because during the winter you need to protect your plants and you need to keep like a certain temperature inside the building. And we're using energy to keep the right temperature inside. So something that we can do is to retake the energy and keep the energy inside the loop. To be honest, we can do. We are doing the same with water. So yes, we are consuming 90% less of water, but also we keep reusing the same water because we are filtering the water. So to answer your question, yes, although we are not super flexible, because the light cycles, they depend also on the plants. So they have a period in which they need to get lights, but also a period in which they need to sleep. So we really need to mix all these things together.
Thank you.
Yeah.
Hi, I have a question related to what kind of crops can you grow in this system? Because you have a system which basically allows you to grow crops in an isolated environment. But I was thinking, do you have any limits of what you can grow? Can you grow, for example, rice or wheat, grain? Yeah, that's my question.
Okay, so the limit is mainly an economical limit, like what is worth like growing inside a farm, because then you have some like the cost is slightly different, and right now we are targeting like top market, like things that a chef like to have because they are fancier and because maybe you really care about taste. But sure, like if you want to deploy these things, I don't know, in third world countries and they need to grow rice, it's possible. So we are really experimenting a lot with new things, like we are trying to grow microgreens, strawberries, and all these things. So yes, to answer your question, it's possible. It's like making money, that's another thing. Okay. Yeah.
I have a question about how much of the environment are you currently controlling? Because from what we've seen, you can control amount of light, water level, and probably the composition of water. But do you also try to control temperature, air pressure, maybe air composition, or do you even monitor those parameters, because they all may have impact on how those plants are growing in different parts of the world, which you already mentioned that the recipe will be different depending on where you grow.
Yes, so just to recap, what we control is, so we control water, so we control the water level inside the farm. We control the air level, so the airflow, and controlling the airflow is a way also to control the humidity inside the farm. We don't control temperature, so we have a temperature sensor inside the farm, but we don't control the temperature. We have pH control and nutrients control. So that those are like the main things that we control. Like the next generation will have more sensors and will be more flexible on this side. But these are like the main things that we can move and the knobs inside the farm. So yes, like you said, it's more or less isolated, although it's not really at the end. Like if we think about like bacteria or like diseases, they're moving around, and it's really hard to isolate them because maybe they're using hair as a medium, and we are not really filtering hair. So that's really hard. Like I said, inside the apps we have temperature control, but it's like building-wise, it's not related to a farm. We are really experimenting with different things. One of the problems is that you need to do all these things like at scales. So what I mean is like, okay, you want to have temperature control, that's fine, but can we do this in sustainable way for 500 farms? And another thing is that we need to build and maintain a software for all the farms. So when you do a release for new hardware, then you need to retrofit things, but also you need to change software to be able to use the new hardware, but also be compatible with the old one. So doing changes inside the hardware, it's pretty tough. It takes like months compared to releasing software. So it will be more flexible definitely with the new generation. Like we learn a lot about how to create proper farms.
Okay, so I have a question. So what is the difference in retail price between this crop that you are creating and growing within your in-farm solution and with comparison to the traditionally grown crop?
So like I said, we target like high market, and the price, to be honest, is pretty much the same. Like if you go to Edeka in Berlin and you compare our plants, our crops with the competitors one, the price is more or less the same. I think we sell the plants for €1.30 each, I think, which is pretty much the same price if you buy like I don't know, like a basil plant, I think. So it's more or less the same. It's not super expensive. Like I will say it's pretty cheap for the quality that you get. It's like it's hyper local, and the main thing is the taste. The taste is completely different because when you get something from the south of, I don't know, Germany, Italy, whatever, then you have like 1 week in the middle between the harvest and when you get the things inside the grocery shop. And maybe they freeze thing in the middle to keep the quality, to keep the color, or they put some like chemical thing on top of that. So really, when you open a farm, you get all the taste, all the flavors. So yeah, quality-wise, it's a good price.
I have a question regards to the IoT devices you were talking about. You are mentioning about a container going to be running within IoT. What type of container it is?
Sorry?
You're mentioning about IoT devices that going to run containers.
Yes.
And what type of container it's going to run? That's what I'm asking.
Okay, so the next generation of farm we developed this new microcontroller inside, which is at the end is a big Raspberry Pi, but we will use Balena as a cloud provider, and inside, because it's like a computer at the end, you can run Docker and you can run containers inside. So you can test the software on your computer, and then you can just ship a Docker image, and you can deploy your image to IoT devices.
Okay, I cannot see any further questions. Any last thought from you, Christian, or you're good?
If you have any other question, I'm...
Okay, thank you very much.
Yeah.
And please go for the coffee break.
Thank you.
You can use the other exit downstairs also.
No, powinno mnie być słychać. Dobra, cool. Dobra.
Hello guys, welcome back after the lunch break. I have a small announcement from the organizer. If you wanted to attend in the 5th session a lecture from Dominic Deja on stage 8, it's not gonna happen, sadly. Instead of, Bjorn Faller will give his lecture called Modern Techniques for Keeping Your Code Dry. Okay, our next speaker is Łukasz Langa. He used to live in California for 5 years, but after that time he decided to move back to Poznań because he was lacking of good pierogis and bigos in United States. Please welcome Łukasz Langa. Łukasz Langa, AsyncIO and music.
All right, thank you. Hi. Today we're going to talk about an asynchronous networking framework written in Python for Python and how we can use that networking framework to make music happen. My name is Łukasz. I come from the internet. You can find me in all sorts of places online. I'm very happy to discuss my previous Facebook employment. I'm pretty sure you have things to tell me about the company. So of course, I do like analog synthesizers, so I'm always open to talk about this. I am serving as the release manager for Python 3.8 and 3.9. In fact, just from the hotel overlooking the university at 2 a.m. in the morning, I released Python 3.9.0 Alpha 1. So it's real. Yeah, I also built a small, humble tool that I always wanted to have, which is an opinionated code formatter called Black. You might have heard of it. So of course, I'm happy to discuss any of those topics. Used to work at Facebook. Later, I moved back, and now I work for HDB, which is a company working on HDB, the product, which is an object relational database. Check it out. It's actually open source. You can kind of check out the code on GitHub. It's AsyncIO. It's proper Python 3.7 code. You know, just try it out. Today we're not going to talk about HDB though. What we're going to do is we're going to discover how AsyncIO can be used to process MIDI. If you've never heard of MIDI, you're going to learn what that is in a second. To drive hardware synthesizers. And because just talking about it would be too boring, we're going to do it live. So, as I already told you, I kind of like analog synthesizers, which is a way to make music using very simple electrical circuits. Those electrical circuits are not software driven, at least not the component that actually makes sound come out of your speakers. Those devices use very simple analog oscillators that are controlled by voltage, and if you give it more voltage, the pitch is higher. If you give it less voltage, the pitch is lower. And so literally you have to tune them. You have to do like all sorts of things for them to sound nice. However, they have this very, very pleasant retro kind of vibe, retro sound that I like. I built a bunch of synthesizers myself. This is a modular that I am sporting at home. However, it's not really lending itself very well to travel. It is rather kind of brittle, and it's very cumbersome to set up after you disassemble it. So instead, what I'm bringing you today is two pieces of hardware by Innovation. Those are production grade hardware synthesizers, both of them. For example, they're used by Aphex Twin for actual live performances. So these might look like they're toys because the blinking lights are very nice. However, they are actually used by real musicians, not me, but like by actual musicians, to drive actual live performances. So in this case, I have two devices with me. So the first one is the circuit, which is a standalone music groove box. It is essentially like a small musical studio on its own. We are going to be using it today as a drum machine. So that this is what we're going to do for it. And the second piece of equipment is a circuit mono station, which is a monophonic analog-based synthesizer. What that means is monophonic, it only can produce one sound at a time. It's analog, so as I said, like there's actually an analog oscillator controlled by voltage that produces sound that later is processed by a filter and a bunch of other things, which are also analog, and then it goes all the way to our speakers. We're gonna be hopefully hearing some of that. And those two synthesizers are in no way connected to the computer, like in terms of audio. They are connected to a mixer I have with me that just allows both of them to just be audible with this nice cinema sound setup right here. So how is this going to work in terms of Python? How is this going to work in terms of the laptop I have in the middle? Well, I'm going to have a nicer graph in the future, but if you're dying to know, the thing is this. We're going to sequence what those devices are doing using Python, using just two USB connections, like for one device each. So those devices don't talk to one another. The laptop is not even sound connected anywhere. It doesn't make any sounds. Everything that you're going to hear comes from those hardware synths. But that's the music part. Where's the AsyncIO part? You might not know AsyncIO. It's a relatively new feature. It's a networking framework that actually is a rather different paradigm of programming from what you're used to if you're using Django, Flask, or something else. So I don't blame you if you never used AsyncIO before. So I'm just gonna teach you AsyncIO in 5 minutes. How does that sound? This is the most important slide to learn what AsyncIO does. I actually had like an entire talk at this very conference 2 years back just to explain AsyncIO. So obviously I'm not going to be able to go into too much detail right now, but it doesn't really matter. Like for what we need, we just need to understand that AsyncIO at its very core, in the very, very middle of it, it's just an event loop. That event loop takes functions, so callbacks, and runs them one after the other. Usually it runs them in response to network events. So if there is waiting data on the line, it is going to respond to it somehow. But you can also just do arbitrary computation with it just by scheduling functions to be run on the event loop. There is just one event loop on a thread. So that means those functions are called one after the other. There's no parallelism right there. There's just a simple loop that calls things, and they kind of wait for one to finish to resume and run something else. So how do you run that event loop? Well, a simple way to do this is just to say, import AsyncIO, get the event loop for the current thread, and just say run forever. Well, that's great, but that does nothing because there's nothing that we registered to happen on that event loop. So how do we do this? We're going to see that in the future, but first I wanted to show you how that event loop actually looks like in AsyncIO's own code base. That code base is open source, so it is absolutely possible for us to look at the source code and learn how it works. In fact, the implementation of AsyncIO that you have in the standard library implements the main event loop in ways that are consciously made easy to understand. That is not the most efficient event loop that you could be using. The most efficient one is called UV loop. You can find it on PyPI. You can just pip install UV loop and use that instead. That is what you should be using in production. But the event loop that comes with Python, it's made to be readable. You can literally go inside and understand how AsyncIO connects things together, why this entire thing works. And let's do that right now. If you go into the AsyncIO code base, you're going to see that in the event loop, there is literally a while loop that just loops forever, as we said in run forever. But the thing that it does inside is just trying to run things once and maybe just break if there is any kind of stop error, which might be you giving up on the program and pressing Control-C, or there might be some exception that was not handled, or any other event that makes us actually not run forever. I'm kind of, you know, not very happy with the name run forever. It's like kind of never forever. Like, was there ever any user of AsyncIO that actually ran it forever? Like, it's kind of weird, but it's what it's called. So if we could actually run things on the event loop, how would we do this? How would we register them? You can schedule things to be run on the event loop by telling the loop that please take this function and call it later. If you're calling it later, you're saying wait at least that much time. In this case, on the first yellow line, it's 2 seconds. Or you can just say call soon, which means as soon as you're done with the thing that you're doing at the moment, please run my thing. Run the callback that you have here. Obviously, the I right there means it's just an argument to the function that we're going to be calling. So this is a way, a poor way, but a way to run things on the event loop. So that sounds great. Okay, you can see on the right side of the slide that what will actually happen on the event loop if we try to run it, there would be 3 things called, like anything of 1, anything of 2, anything of 3. 2 seconds would pass and the loop would stop because we told it to, right? So a nice stop error would be arisen and the run forever would again not run forever, in fact. So this sounds great, but AsyncIO was created to allow us to do a lot of concurrent things, to make things happen at the same time, at least perceptibly. But as I already told you, and this is true, there's just one event loop, and it runs things one after the other. So if any of the callbacks is time-consuming, it is time-intensive, everything else is going to have to wait until that particular callback is done running. So if that is true, then how can we ever achieve any sort of concurrency using AsyncIO? Well, let's start with not using regular functions, but using coroutines. What are those? You run coroutines by defining async functions. So you're going to sprinkle async and await on your code, but essentially what is happening in our callback right here is we're inserting async, which means we're having an async function, and instead of using time.sleep, we're using a coroutine version of it, which is asyncIO.sleep, and we're awaiting on that. So below you see like 3 awaits, which means things are still going to be run one after the other, and that doesn't really achieve any concurrency yet, right? But having this building block of a coroutine, what we can do is we can gather 3 callbacks in a way that they're going to be awaited on perceptibly at the same time. And if you run this, then you'll see that essentially the prints just come out at the very same time. Like, it's perceptibly very quick to run. So these are the main blocks that we're going to use today. We're just going to be gathering a bunch of things. We're just going to be awaiting on a bunch of things, like, you know, and it's going to be nicely perceptibly happening at the same time. In fact, if you're wondering now that what is this sort of magic? Like, how does async and await actually work? We can, again, just look inside Python, which is open source, and see how those things are built. So when you're creating a coroutine instance by just saying callback 1 or callback 2 or callback 3, if you're not awaiting on it, like we were on the previous slide, right? We were awaiting on callback 1. We were awaiting on callback 2. If you're just creating them instead, they're not actually running it. They're just instantiated. And what is instantiated is a task. And that task, in its init, at the very end, just says, please call soon one of the steps that I have inside. So that same call soon that I showed you at the very beginning is a building block of the coroutines. So what is that step _step? again, we can look in the source code, and what we're going to see is that essentially it is running a generator until the next iteration of it. And it's doing so as long as there is no result or there's no exception. And it's just registering itself again after running at the back of the loop. So now you have to understand one thing, like coroutines are implemented as generators, which means they just live. They're not being destroyed by Python before they're done. And they are being executed until one await is found. And then the event loop is going to run something else that it has scheduled at the very same time. So this is something that is going to look something like this on a graph. We're going to run a step of the coroutine 1, a step of coroutine 2, a step of coroutine 3, and a round robin. We're going to go back to coroutine 1 because as soon as it was done with the first step, it registered itself back on the event loop, and so on and so on. So by doing so, we're no longer waiting and holding the entire interpreter hostage when we are kind of waiting for an external event to happen. Instead, we're just saying, I'm waiting, so just go ahead, do your thing in the meantime. I'm registering myself at the back of the loop if a new thing happens to us. So that's AsyncIO for us. We're going to use await, we're going to use async functions, and we're going to gather them so that we have a perception of things happening at the same time. So what is the network protocol that we're going to talk? We're going to talk MIDI. But before we get to MIDI, I don't blame you if you're not a musician and you don't really read music, you never played an instrument. So let me show you this. In music, the most basic thing that we care about is pitch. Pitch means how high is the note that we are playing or hearing. So there is a notation that enables us to just agree between people how high a given note is. And that notation is like on the very bottom here of the slide, but it also has like, nice ABC names for all the notes that you're seeing here, right? So there's C, D, E, F, G, A, B. In Poland, like you would actually say H and not B. I don't know why. But those are the basic white simple notes that we have. And there's also some more like enharmonics, like the black notes on the piano. Like we don't care like about those at this point. What we care about is that the C, D, E, F, G notation is just telling us like, oh, this is what note that is. And like traditionally, there's going to be like C0 means it's rather low, and on the keyboard C2 is going to be higher, C3 even higher. So we're just kind of adding digits to it to know which octave, like how high we are, because the notes repeat actually, right? If you ever saw a piano keyboard, the keyboard is just very regularly repeating every 8 bass notes, right? So this is exactly all that you have to understand about music for the purpose of this talk. One last thing though, in the notation below, you see this very fancy key at the very left, and there's like 2 numbers there, like 4 out of 4. That means that the bars, like the timing of that particular piece of music is counted in 4 quarter notes. We can see that they are because every 4 quarter notes, there's going to be a vertical line saying, oh, we're done with this bar, we're going to go to another bar. So this is how we organize music time-based. I guess this is all that we need for the time being. So let's move to MIDI. There are many standards about networking. There's many standards about interconnectivity between things. And MIDI is amazingly one of the standards that actually worked. People in the early 80s decided like, hey, you know what would be great if we had a way to connect 2 pieces of music hardware and have them talk to each other. So one can play notes on the other, or like they can play at the same tempo, like they can do things together. So a standard was created, and it's still like very popular, like even like the very, very basic 1.0 versions from like 81, I think, which is basically a way for us to tell a device to do a thing like as soon as possible, like right away. In other words, it is a synchronous protocol to talk to devices one through the other. Historically, we've been using DIN5 cables for them, as you can see like right there. Those were rather flimsy to use because they're like unidirectional, meaning like one cable only informed one device about things that should happen coming out of another device. But if you wanted for this communication to be both ways, you needed a second cable for this. Like another problem was that those cables like were never really durable. They had like issues with length and how far they could go. So hopefully, like we're gonna get rid of them at some point. And today, in fact, we are already in a world where most musical hardware using MIDI is using USB cables. So this is what we're going to be using today, like with this laptop, right? Like USB cables also have this great feature of being bidirectional. So there's just one connection that enables us to communicate both ways, which is great. We're going to be using that. So okay, so like what kind of messages, what kind of packets go through those cables then? Like the protocol is super easy actually to understand, like which I'm very happy about. Like it's rather trivial to explain, and it's rather trivial to see it work in practice because it's synchronous. So there's literally messages that say, please play a note on a given channel of a given pitch with a given velocity right now. It's a synchronous protocol. Like it never schedules things like in the future. It just says, now, do it. And then if you want to kind of raise your hand from the keyboard, like stop playing a note, you just send a note off signal, stop playing that note. We have channels in the MIDI protocol so that you don't need 16 cables if there are 16 voices that a given instrument can make at the same time. That would just be too silly. So there is support for channels. And historically, the important piece is that the channel 10 is just percussion, is drums. This is what we're going to use. Like all the other channels are like whatever the devices have configured. So there's going to be note on, note off events. Like simple as that. It just goes one way. If you want to have a connection the other way, there's going to be kind of another connection where you send things in. And one particular thing that we're sending all the time is the clock signal. The clock signal tells us how fast should we be going. If we know that there's going to be 4 quarter notes per bar and we're going to be playing some music together between devices, what we need to understand and we need to agree on is how fast are we playing. So again, this is a synchronous protocol, so it's literally just sending 24 pulses per quarter note to inform devices between each other that like this is how fast we're going. And between them, you can also just say start, which means if you have any sequence configured, if you want to do anything, do it now. And if you're sending stop, that means whatever sequence you were playing, give up, like let's have silence for now. So having all this boring theoretical knowledge now in your heads, we can go and proceed to actual like practice part, to actually see the demo of what I wanted to share like all along, but I had to have this kind of introduction so that we are on the same page. What we're going to do today is we're going to use the drum machine and we're going to use the monophonic bass synthesizer as instrument sequenced with Python from this laptop right there. So the connectivity that we're going to be using is through MIDI cables, like those are USB cables. But what we're actually going to do is Python is going to send a MIDI out signal to both of them, like one connection each. And we're going to be using, just to make it a bit harder for ourselves, but also kind of more useful for actual production use, we're going to be using the clock signal from one of those hardware synthesizers. This is actually pretty interesting because what that means is that the code that I'm going to be showing you is less of a toy than you might think. You might actually be using this to interface with other synthesizers that you have at home or keyboards or whatever else. Because you know that that code is able to go as fast as this hardware that you have does. So you can do stop, you can do start, you can slow down and speed up, and it's going to keep in sync. So that's it. Let's see some code. In fact, the main function of the program that we're going to go through fits on a single slide. So I'm just going to go ahead and before the demo part show you that right away. So we're on the same page like what the program is going to be doing. So first of all, like there is this asynchronous main function. For the first thing that we're going to be doing is we're just going to get some ports out of some MIDI library that we have. Getting that ports allow us to just kind of assign some names, assign some connections to the cables that I have on either end of the laptop, right? Like we really need to understand like where are the connections. So the API is actually very nice. Like those objects, like you know that I have here physically have nice names that are very easy to understand. They really map to the names of those devices. So we can just ask for a port of the circuit. We can ask for the port of the circuit monostation, and we're going to get a pair each, right? Because a USB connection is bidirectional. So once we do have this, what we can set up is a queue of MIDI messages that we're going to be getting from, say, the circuit, right? Like we said that we're going to be listening to the clock signal of a hardware synth. So this is how we're going to be doing it. We're going to have a queue where signals that the circuit is sending us is accumulating. And then we're going to be using AsyncIO to consume those things on the queue. So to do this, just as you saw in slides before, we're just getting the event loop there, right? We have the event loop object, and we can now just say, like, hey, whenever we are getting anything from the circuit, that's the last line right there, please call this function, please call this callback. And that callback, as you can see, is going to just call soon a thing on the event loop. And that thing is just put the message you just received on the queue that we have, so that coroutines on the other end can now consume it and just do nice things with it. As you can see, there is no async between the MIDI callback def, because the MIDI library that we're using is a nice Python wrapper on top of probably the most kind of production-grade MIDI library that there is, written in C++. So that library is running its own C++ thread, just looking at the signals that hardware is sending. And when it's sending it, it just allows us to register callbacks to do things. Those callbacks are not going to be running on the main Python thread, which is why we have to run call soon thread safe instead of just a regular call soon on the event loop. But that's all good enough. This is just plumbing so that now we can kind of pretend that the world is fully asynchronous from now on. It's fully AsyncIO from now on. But before we get to the nice coroutines, like let's do some more kind of chores. Let's clean up the situation. First of all, we're going to close the port that comes from the mono station. We're not going to be using any signals that that piece of hardware is sending us. The reason why we have to close it is that, as I said, C++ has its own thread where it is consuming those messages, and it would soon fill up whatever buffer it has and be very unhappy with us for not consuming it. So we are informing it right away. We won't be using information coming from this device. We're only going to be talking to that device. All right, and then we're going to have some magic data class performance that I'm going to show you soon. And we're just going to run this MIDI consumer that we're going to look at next, kind of forever. I didn't use the word forever. I don't like it, but it's what is going to happen as long as we're not pressing Control-C, as long as we're not quitting this entire endeavor. The MIDI consumer is just going to consume whatever there is on the queue and use the performance object as sort of, state for this particular program. So, of course, the most important part and most interesting part and why we are all here happens inside the MIDI consumer. So let's look at that. This is hopefully like very easy to understand, which means it also fits on a slide. Without further ado, this is it. Like it is literally another for loop, another while loop that just goes on forever, and it's just getting things off the queue and recognizing what they are. If the message that we got on the queue is a clock signal, we're just going to say that, the delta between now and the last clock signal that we had let's just store it in the performance object. We're going to be using this to time now, right? Like we're going to be using to time the performance. If it's start, means, we actually want to play our sequence that we're going to program next. So let's create the task of the drum machine. If we are stopping, if we're going to press stop here, just cancel the drum machine, delete it, this is it. The reason why this start and stop is nice is that we are actually creating AsyncIO tasks, we're destroying them, but that also means we can arbitrarily start and stop our performance without restarting the entire program. We can just kind of react to real-time events that way. So there's a clock, there's start and stop. This is the incoming signal from the circuit that is going to tell us how fast we should be going. So the drum machine, how much code is that going to be? Is it going to be an entire slide? Maybe it's going to be more. Well, it's time to find out with the demo. Let's do it live, as I promised. So we're here. I'm not going to be saving whatever I did here. We are in the directory of the project. Just so that you know how big that project is, let me just show you the tree of it. So the project is very simple. It's called AIO, which is like AsyncIO, and tone is just tone. We're going to be making tones. The file we're going to be looking at now is just main py. Let's just open it. Main py right here. So the main py file, we're going to be talking about this like in a second, but let me just make the font a bit bigger. Is that big enough? Yes, okay, cool. The performance object, as you can see, is a data class. It doesn't do much of anything. The only thing that we did to kind of have abstracted away some very boring things that happen in MIDI all the time is we created some helper functions to play a drum or to play bass, because bass is going to be this thing right here. And that play is literally a function that just sends MIDI messages. You saw the MIDI messages before, right? We can really say, like on our MIDI connection, please play a note. And then we can say, please stop playing a note. So the only reason why we have a nice play function is for us not to have to use this kind of weird bit notation all the time and whatnot, and just be able to say play on a given channel, play a note of a given pitch for this many pulses with a given volume and some other details. So that's it. And also sometimes you don't want to actually play, you just want to have a rest. You want to have silence for some amount of time. So we just have a helper function that just waits. It's just going to use AsyncIO sleep, as we saw in the example before. AsyncIO sleep for this many pulses. Okay, good enough. So now having our main function, we're going to be using UV loop because production, and we're going to be running our async main that you already saw. And we're going to have a MIDI consumer that you already saw. And this is our drum machine. I know it's a lot of code. It looks scary. But it's really all we need. If we have this, we can now start playing music. So let's see, without further ado, if any of this is going to work. So now is anything playing? No, it's not, because we didn't press start. We are clocking the performance from a hardware synthesizer. So now nothing is happening, even though you can already see that all the events going there means at all times the circuit is telling us how fast to go, 24 signals per quarter note. But we didn't press start, and we programmed before that we are only ever going to create the drum machine once we press play. So if we do, we have a rather simple performance here. It's just a while loop that is literally just playing a drum every 24 pulses, which happens to be exactly a quarter note. So that is actually pretty boring at this point. It's not very interesting, like in any way. So can we do something more impressive? Well, we can. Let's stop that thing for now and add some more code. For example, if we said that we want to play a snare drum every second note, what we're going to get instead is something just a tiny bit more interesting than what we had before. Okay, like I know I'm no Daft Punk, but like it's getting increasingly similar to actual music, doesn't it? But it's still rather kind of boring. But let me just use this opportunity for you to show you what would happen if we slow this thing down on hardware or sped it up. So as you can see, it already responds to what we're doing in hardware, which is pretty sweet. If we press stop, it stops playing. If we're pressing start, it starts playing again. Okay, there is some basis, there is some hope that there's going to be something more interesting happening soon enough. So now, obviously, we have Flake 8 yelling at us like, hey, you're creating variables and you're not using them. Like, you know, kind of clean up your life. So let's use those hi-hats. But what I would want to do, like if you ever saw a real drummer, like they can play the bass drum and the snare drum at the same time they're playing the hi-hats. But here I just have a while loop that doesn't do much of anything. So what can we do here? Well, how about we actually create an internal async def here saying that this is our bass drum. It's going to be our bass drum. There's going to be a while true loop here. And that's going to be the bass drum from here. Okay, cool. And then we're going to have a separate one for the snare, which is also going to just play the drum. But if we just play like this, we're just going to be hitting the bass drum and the snare drum at the very same time. Kind of know what we want. So instead, let's just say that instead we should be waiting here. And the wait should be for also 24 pulses, meaning like the snare drum is just going to wait for a hit and then hit, wait for a hit. Cool, good enough. So next thing that we're going to do is we're going to create another async def for the hi-hats. Having this now, we can just say let's play closed hi-hats twice. This is gonna be kind of simple, but more interesting than it was before. And let's play them like rather fast, and then give us some space with the open hi-hat, so the open hi-hat can actually kind of reverberate for a bit. Okay, so now we have 3 coroutines. How can we make them run together? Well, we saw already. We can just await on AsyncIO gather of those 3. So we're just going to instantiate our bass drum, we're going to instantiate our snare drum, and we're going to instantiate our hi-hats. Having those 3 things together, we're gathering those. Things should be happening. All 3 are while true loops. Things look good. Flake8 is not yelling at me. Let's try it out. Okay, I need to press start. All right, we're hearing things happen concurrently at the same time. Why? Why is it possible? There's just one event loop on one thread. There's just one cable going to the circuit. So is it really happening in parallel? Well, no, it's not. It's just a stream of events. But if they happen close enough to one another, it is perceptibly the same thing. As you can see in the latency that I'm showing here, like it's like microsecond precision. So essentially, it is not distinguishable for a human being from being actually at the same time in parallel. All right, so we're having this thing, and it kind of doesn't sound awfully bad. Like if you are a musician, you might hear that there's something not quite right with the clock. We're going to be talking about this in a second. But for now, I just want to stop this to not bore you to death with this 4 on the floor beat. Instead, now having this, we can use Python to create some variation. And if you're creating some variation, if you're creating a project in Python that is going to be successful, what you're going to do at some point, like always, every time, you're going to be importing iter tools. That happens every time to me. So we're going to be importing iter tools, and we're going to be using it here to just play with the bass drum for a bit. For example, What if we don't want to play this bass drum at the very same volume at the same time? We just want to cycle through a bunch of volumes. So we can define those volumes, say, one volume could be 127, another one could be like 64, another one could be 32. Or in fact, maybe we can even just do a 96 in between, so there's 4. So now instead of, yeah, Flake8, you're right, we're not using it yet. Instead of a while true, we can just say for volume in itertools, cycle through the volumes. And having this, we can just say, please use this particular volume that we have right now. Okay, this looks good. Let's see what is gonna happen now. Nothing, because we didn't press start yet. We can hear the bass drum kind of going back and forth, but that gives me an idea. If we speed it up, that is gonna kind of sound like an echo, like reverberation. So let's do that. Let's just tell it to just go faster, not a quarter note, but half a quarter note, a 16th. So let's go there. Okay, oh, yeah, an 8th, of course, not a 16th. Okay, kind of sounds like echo now. But what is very interesting in kind of electronic music are polyrhythms. Polyrhythms is a very simple concept. It just means there are different things happening at the same time, counting in different times. And just having two things not being like in sync time-wise, but at the same time still like measuring the same pulses makes for very interesting sound effects. So for example, if we just remove one of them, now we just cycle through 3 steps and not 4. So just having this, let's see what interesting things we might achieve. Okay, that sounds a bit more interesting now. And we can, in fact, like maybe kind of like do some like trappy rhythm if we just slow down that snare drum as well. So if we make the snare drum slower right here by twice, this is gonna sound like more hip-hoppy now. Let's see what we can do with that. Right? And I mean, like, I'm no Jay-Z, but like it kind of starts sounding cool. So what the purpose of this exercise is to show you that like all this code is just regular Python. It's trivially easy to understand what is happening just reading it from top to bottom, and yet through the magic of the gather right here, it is playing like perceptibly at the same time, perceptibly in parallel, and like doing already a rather complex sequence. But if you're listening to it now, like, is it really in sync? Are the coroutines in sync between one another? No, they're not. This drummer is really bad. Like, things are not where we want it to be. So what is happening here is called clock drift. Clock drift happens when you are counting on a given piece of hardware the timings between pulses, and some other piece of hardware, or in our case, there's just different coroutines, are also counting pulses, but they never recheck whether we are on the same page. So they drift away, and it's clock drift. There's literally a Wikipedia page about this thing, because it is something that happens even to production hardware, and there's like very cumbersome workarounds for this. So obviously, we would not be able to use this in any sensible form if we had to like kind of bear with this unbearable back clock drift. Like that really means like, you know, we should just pick up some other career. Like, you know, we're not gonna be successful musicians with this. So instead we have to fix what we're doing with timing now to be a little smarter. But what are we doing now again? So the current way to just count how fast we should be going is just to hold the delta between two pulse signals that we got from this circuit. If you remember correctly, like the circuit at any given point in time, always, every day, all day, is sending us 24 pulses per quarter note. And we're just storing the timing that there was between that pulse delta, between those pulses, as a delta so that we can use it, first of all, to when we're playing, to wait for a given amount when the note is playing, and then as that note is stopping, we can wait for the rest. And same, if we are resting for the entire thing, we're not playing anything, we're also sleeping for a given amount of pulses, right? So that sounds like it should be fine, but the problem is this delta is never perfect, and the time that we are taking it might not be the perfect timing that like the device is actually sending us. What you have to remember is this is a synchronous protocol which is sending things as they happen, and of course there's always some latency. My MacBook might decide to like start updates or whatever else. So like this is never perfect, so that will never work. But we can do something better. We can teach you something new about AsyncIO and solve this problem altogether. So let's go through this. However, there's a bit of typing involved, and I don't want to kind of like be very embarrassing like making typos here. So let me just show you what that particular thing does. For now, let's just check out whatever we have here. See, I'm terrible with typos. If we're doing second step, that's the full drums, we already saw them. We're gonna go back to like those kind of boring like techno 4 on the floor drums for the time being. And now we're introducing a metronome. What does that mean? Like how does that look? Well, in fact, there is not much happening here. We're gonna look at the metronome class in a second, but the change that we're gonna be doing is instead of holding a pulse delta as we were before, we're just gonna hold on to a metronome object, and whenever we need to wait, we're just gonna let the metronome wait for us. And for us to understand how long the metronome should be waiting, we're just gonna tick it every time that there is a clock signal. We're just gonna say tick, 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 tick. So we're no longer looking at deltas between two pulses. We are storing the ticks. And when we're starting, we're just restarting the metronome so that the starting point at the same time is also synchronized, okay? Cool. So that is essentially what is happening now. Like, in fact, see, like there's some less code that we have to do now because of this. And let's look at the metronome class. Is it scary? Is it gonna be complicated? I hope not. The metronome is another data class. I like data classes, and if you don't know data classes yet, you should be using them for everything. Like you might also use the pro version of them, which is adders, but they're the same concept. Essentially, what data classes allow you to do is to just specify a bunch of attributes, and this magic decorator is going to create a dunder init method for you. It's going to create a good dunder wrapper. It's going to create like equality, hashability, like other things for you in a correct way. It won't forget. It won't kind of update one dunder method while forgetting about another. It will always be correct and without the boilerplate. So data classes, great. What we're using it for is as well to specify nicely what types given things are. This is useful because first of all, it's documentation. Second of all, that allows us to actually kind of inform the data class creation on like what thing to expect. For example, in this case, we're saying it's just a factory of list or a factory of a lock. So every time we're going to create a metronome object, it's going to create an empty list for countdowns, and it's going to create an empty, a new countdowns lock for us. Okay, so that's data classes for us. What about the wait? The wait is using a countdown. That countdown is gonna just go down to like the 2-0 from wherever we are with the pulses that we're counting, and then it's just gonna be letting control back to AsyncIO. So with a given countdowns lock, we're just appending the number of countdowns and awaiting on them. How does this magic thing work? Like, why awaiting on countdown is taking from the number of countdowns that we should have? Well, it's actually pretty simple. Like the way it works is a countdown is an AsyncIO future. New concept. It's nothing. A future is a promise that something is going to have a return value in the future. So having a future means I don't have what you want now yet, but if you await on me, I'll let you know when it's ready. I will let you know when it's ready. So what we need to do here is simply, when we're ticking, we are ticking down on the value that we have. And if that value is 0, and we have not yet let people know that it's 0, then we're setting the result. We don't really need any result now, so we're just setting it to none. But this is how we are saying that this future is done. So if you are awaiting on a future, but it's not done yet, it doesn't have a set result, that coroutine is going to just keep waiting for it. It's just going to keep waiting for it. But as soon as the set result is done, if any coroutine was awaiting on that countdown, now it will continue. So that countdown allows us to really be synchronized with the tick. There's some just a bit of more code here, but the only thing that is happening really here is that we need a countdowns lock so that if many things are happening at the same time, like we're not going to destroy the list that we have here. It's really just kind of housekeeping. But the metronome is using a concept of AsyncIO, which are futures, just to show you this line. That is the most important line, that you can await on futures. And the futures are going to kind of set a result and let the flow of that particular thing go when the result is set. And we can wait on that same countdown with many coroutines, meaning we are always gonna stay in sync. So let's see if that sounds any different now. Okay, it's pretty much in sync. Let's pick up the speed. Sounds in sync to me. And in fact, you have to believe me that, like, if you left it for hours, which I did testing this talk, like, you know, in the past, never goes out of sync. It solves the problem perfectly because we used synchronization primitives, and the simplest one that there is in AsyncIO, the future, to make sure events are happening, like, you know, in unison. They're not in parallel, but they're perceptibly in parallel. All right. So having this now, you're probably wondering, like, you know, hey, he brought another instrument, but he doesn't doing anything with it. So let's introduce that one then. If we had already our consumer like react to a start by creating a drum machine task, maybe we could do the same to play the notes on this guy, on the bass synthesizer. So let's do that. To speed things up just a bit, let me cheat with Git again. So having this, what you just saw is boom. Now, next to the drum machine created at the start signal, we're also creating a bass line, right? And when we're stopping, we're saying all notes off on the drum machine, we're deleting it, and same for the bass line. We're just saying all notes off, delete the bass line. So how does the bass line look? Is it also as terribly complicated as the drum machine? Well, yes, it is. So that's our analog synth. This is what we're going to be doing with this. For now, we're just playing the C2 note over and over again. Sounds great. Let's try it. This is sound coming from the synthesizer. It's a hardware synthesizer that has many knobs. Let's try them out. So there's a filter here, there's some distortion that we can use. There's a keyboard here, I can also use that one to kind of make things more interesting. Right, okay, it's a hardware synth. The bass note is being sent dutifully by AsyncIO. And we can do like stuff with the filter or whatever. Okay, we're gonna let them go for now. But remember, we did like some rather interesting polyrhythms with the drum machine. So can we do anything that is interesting with Python that also utilizes this and kind of build something rather complex with minimal number of lines of code? So yes, we already used iter tools, which what it gave us is cycling through things in a predictable order. But we also have the random module. We can do things that are a bit less predictable, but also funny. So without further ado, we can change this analog synthesizer to still play our keynote. That's what we were doing before, that boom, boom. And the decay here means like we're really spending all the time possible for this particular like note to play. In the real world, if you're playing the piano, you never play a full quarter note. You're never playing a full note or whatever, because you always have to just pick your hands up, do something else. In this computerized world, we can have hands that are so sticky that we're playing the full kind of amount of a quarter note. So let's have that for the time being. And then we have an arpeggiator. What arpeggiators are algorithms, devices, or pieces of software that allow us to play given notes. For example, those three that we have here, there's going to be a C, there's going to be an F, there's going to be a G, and then, do stuff with them. Like sometimes they're predictably just going through those notes in a cycle, which we're already kind of doing here. Fine, like we're going to be doing that. But we can modify things like what octave we're playing on. So maybe go higher or lower, or maybe go like change the volume. Like we're going to do that next. But for the time being, let's just see whether anything here makes sense, whether that sounds in any way interesting. But before we begin, wait. I said that this is a monophonic analog synthesizer, meaning it can only, play one sound at the time. So what does that mean for me to just have two coroutines now, to have a keynote and an arpeggiator playing at the same time? Well, every now and again, I do have a wait here, right? Means this arpeggiator is not doing anything now. So when that happens, we're just going to be playing the bass note. And when that is not happening, we're going to be playing whatever whatever arpeggiator has in stock for us, for whatever length it has for us at the time. What this allows us to do is, with synthesizers like these, you can glide between different pitches when you press two notes and hold on to them. Don't kind of let them go. So we're going to try some of that in a second as well. So let's hear this. That's kind of, getting closer to the end of the talk. So let's see what is going to happen now. There's an arpeggiator. Wow, that is, okay, cool. It's playing stuff for us. See, no hands. What I can do is, I promised you glide, so let's try some of the glide and see what it's going to do. Okay, it does glide, right, between notes. Maybe it can glide a little less. Or we can configure the tempo here, see, it's also in hardware. So this is something that actual musicians can use for actual performance to just automate things that have to happen. And MIDI is also used for visuals. It's the same very simple protocol. So you can create an entire live set doing both like lights and kind of video and music just using that. But I also promised, if you actually listened to or read the description of the talk, to show you that some of the melodies that we're playing might be informed by the player. For now, I was just pressing play and just kind of being playback Mariah Carey to you. But I want to actually just play something, on the instrument and have it actually do things for me. So we can change what we have here just a tiny bit. And when we do, let's see what is different actually. What we're going to do is we're going to store the last note that was played and use that note here in the bass note instead of that C that was just the bass note that we used before. So the arpeggiator is still running on its own, but the bass note is going to be informed by me playing the circuit now. Let's see if there's any audible difference now in what we had before. There's not, because I'm not playing anything. But if I start, I hope you can hear that actually the bass is changing pitch now. The bass note is changing pitch, right? Oh, listen. That's pretty cool. All right. So what we have here is it is responding to my own input now. And what I can also do now with, if I think about this correctly, this is a full groove box. It's a full device that can not only just play whatever I give it, but also play sequences of its own. So what I can do now is play a stored sequence. See, no hands. It is playing what I just played before for you. And using this opportunity that I don't have to do anything anymore, I can just go and play another synth. So just like to do what every musician wants to do, and everybody is kind of groaning now, solo. All right, that was AsyncIO and Music. My name is Łukasz Langa. Thank you very much.
Thank you very much, Łukasz, for your lecture. Sorry, but we don't have any more time for the questions. So if you would like to ask Łukasz a question, just join him during the coffee break.
Cool.
I'll
be around both days.
I have two announcements. First, that you can rate those lectures on CodeDive website. And second announcement is that Dominik Deja won't be able to give his lecture at stage 8 during the next session. Instead, Björn Faller will give his lecture called Modern Techniques for Keeping Your Code Dry. Have a nice coffee break. Thank you.
Hello? Hello, hello? Test. Okay.
Hello guys, after the coffee break, it's very nice to see you. I would like to start with some rules. First of all, please put your phone into the silent mode. Secondly, please don't leave the stage, the room during the lecture. And further, if there will be any questions and we will still have time, I will be near the exit and will take questions there. Our next speaker is Mateusz Dymiński. He is working at Nokia, and on daily basis he builds scalable distributed systems in a cloud environment. Please welcome on stage Mateusz Dymiński with his lecture Diagnose Your Golang App Anytime, Anywhere. Diagnose your Golang uptime anytime, anywhere. Mateusz Dymiński.
Okay. Hello, everyone. So my name is Mateusz Dymiński, and today I would like to talk about diagnosing Golang applications. And if you don't know Go, you shouldn't be worried, because all the examples are pretty straightforward. And I mainly focus on tooling, so some really nice tools all around the Go, which might help us to find the problem and also improve the speed of our applications. So let's go. About me, as I've already have a introduction, but I came from the Java world, then switched to Go, and in the meantime I'm organizing the Go Wrocław, which is Golang meetup here in Wrocław, so please be invited. You can find me on GitHub, Twitter, and LinkedIn as well. So if you have any questions, also if you would like to find the slides and all the examples which I'm going to show today, please visit this this page. Okay, so the PPTX document, slides, code examples, everything is there. It's already been there for some time. So so if you would like to have some and make some photos of the slides, so I guess it's better to just visit this this page. So let's go. About the agenda. So I've split it, my presentations into three things and three parts. So the first and the place where we start is debugging, then profiling, and at the very end, tracing. So all those three things might help us with find a problem, okay? Sometimes it's a performance problem, so the profiling and tracing might help us to find a bottleneck in our applications and improve it. I will do that during the demos, which I'm going to show you. And the first part, the debugging part, is focused on finding the problem with the logic. Okay, so if we've got some of course some bad things in the code and so wrong path, wrong if, wrong for anything, then debugging might help, of course. And debugging, of course, the definition is pretty straightforward. So let's go to that. It just allows us to pause a program and then examine its execution. Yeah, so we can check what is going on, what are the state of variables, what's the flow, where we are going to do next, and so on. Pretty straightforward. So let's go. Let's assume that we've got a simple server, HTTP server, which has only one handler, and this handler adds some values. Okay, so when we hit the server and with the method /add, we pass the vals, we should get such output. So let's do that. Okay, and also the handler itself. Okay, so before we start, and I'll show you the demo. Here is exactly the implementation of this handler. So we are getting the query args, the vals, splitting that by the comma, and then in the for we are just adding that to the accumulator, and then flashing everything to the response, and we've got the results and the sum of blah blah blah, the values. Then is that. Okay, so let's do that. And okay, let's check it how we can do that, and then we'll go to old way of debugging. But let's start our application. So here we've got this handler. Here we've got a main function, as I've already shown you in the presentation, and then we are showing the results. Okay, so let's hit some breakpoints and run just run it. I'm using the Visual Studio Code, but it's pretty straightforward to use any other ID. Okay, and then let's go to and hit the curl. Now we see that we can check the values. Okay, let's continue. Checking the output. Here we can see that there is a result. It's sum of 1 to 4. It's 7, of course. So everything is working. Okay, but some time ago, before the Delph, which is a debugger which I'm using, there was an old way of debugging. And the old way of debugging, which was told to me by my friend, was to just print everything to the output. Okay, so my friend, at the very beginning, when I started using Go 6 years ago, he told me that there is a no debugger. In fact, it was, but it's not very common at those times. So he said to me that I should print everything to the screen, yeah? And he said that that's what real hacker does, yeah? So that was my first experience with debugging in Go a few years ago, but we can do better, yeah? So the very first thing is that we've got two options. The first one is the GDB, and the second one is Delph, as I mentioned already. So the Delph is the debugger which is written in Go, and it has great support for a Go runtime. But when I was preparing this presentation, then I started with the GDB. So I said, okay, there are two debuggers, let's show two of them. Okay, then I entered the web page, which is official documentation from the Go creators. Then I read it, and there is a two nice sentence, okay? The very first thing is that the Delph is a better alternative, and the second, that GDB does not understand Go programs well. So I said, okay, let's leave it. So let's focus on the Delph. How to do that in Delph? So what Delph does under the hood, it's a bit more complicated than just running the code and then attach and go via the breakpoints or debug the flow. So the real and the true under the hood is that when we call the Delph debug and then our path to our application, under the hood it compiles our program, but in not a regular way, but in most suitable. I will explain that later. Then he executes this program and then attach to this program and begin the debug session, okay? So that's pretty straightforward. The demo, I show you that it's really easy to start the debugger here. The very important thing that there's a configuration of that, but this one, the one which is called launch, it's like by default in ID. So if you've got a Go plugin in VS Code or in another ID, you've just got this configuration. It will allows you to debug the program. It's going to install Delph under the hood. So Visual Studio Code says that, okay, you need to install Delph fast because we are doing Delph. Okay, and you can do that automatically and start debugging. Pretty easy. And as we can see, and as we saw in the previous example, it just works, yeah? We can run it again. And we can, for example, check also here. We hit the breakpoint. We can, of course, see the values, nothing special. 1, 2, 3, 4, 5, 6, 7. And then in the loop, we can calculate them, yeah? Pretty easy. Usually, Chrome does 2 requests. That's why we hit the breakpoint twice. When we test it with the curl, it does only 1 hit here, okay? We can continue, and ta-da. It's working, yeah? So really, really easy for a warm-up, okay? Let's go down. Let's go. Remote debugging. So it's when we have some production server we would like to attach to this debugger remotely. It's a bit more complex. So what Go needs to do to be able to be debugged, the program, we need to build it with some extra special flags. So if we call Delph and run, then of course it's going to do that under the hood. But in the Go 1.11, we started the whole dwarf things are compressed, so we need to pass extra flags to do not compress them. So the binary is a bit bigger. There are some compiler optimizations are missing, just to make it more and debugger friendly. Okay. And then we need to run applications, and then we can run another process which will attach to this speed and then have a control over the main application. Okay, so that's what we need to do to be able to debug Go programs remotely. Okay, let's let's do that. Okay, so now I've got already prepared the version of App Mac, which is our application is already built. So let's run it. Okay, we need to turn off the ports because they're the same. Okay, so let's run it again. Okay, it's working. Let's check whether it's working with curl. And now we need to attach. I'm using this also p grep, which is just getting the PID from the name of the application. Okay, so now we are running the Delph. We are telling him to attach with the headless mode, just to not run this application itself, but just to attach to the other one, and some parameters like accept multi-client, just to allow the reconnection. And then we can run it. Okay, now we see that it's working. We can hit the curl, and nothing is happening because by default Delph is waiting for setting the breakpoints. Okay, so let's do that. So we are changing this launch to remote on localhost, and this configuration is just this one. So we need to pass the directory where our application is and where are the files, the Go files, which can understand the application itself. Okay, and then the port. Sorry, this is remote on localhost. This is workspace root. So this is the directory where I run the Visual Studio Code. Okay, and then I'm passing the port on which Delph is listening by default. Of course, this is this port which is where it's run. Okay, and now when we run it from Visual Studio Code, okay, let's debug that. Switch it to remote on localhost. Yeah. Let's go. Okay, and we see that this request from curl was in the idle state, so it was waiting for an application to go, and now we are just hit the breakpoint. Everything works like a charm. Okay, pretty easy. So let's go further. Okay, now let's have another thing which is pretty common nowadays, just to try to debug Go applications, but in the Docker. So what might change? So to do that, we need to, by default, the Docker doesn't like two processes run inside the container by default, and I guess that's the best practice is just to run process there. So we can use Delph, which will have an extra method which is called exec, which will, when we pass the binary, which we previously built, so we run this go build minus gc flags just to skip the optimization of the compiler, and then we run Delph, but inside the container. Okay, that's the whole magic which we need to do to remote also debug the Go code, but inside the Docker. Okay, to do that we need to run the Docker, but it doesn't work. And why? Because by default Docker has security options which forking the exec and the speed and getting access to the main process is not allowed. Okay, and to do that we need to set extra options. So we need to pass this minus security opt seccomp unconfined, and then Delph can run Delph server, and next the Go applications then attach to the speed and control the flow of our application. Okay. So let's go, let's do that. So I'm running this Docker. Okay, and again, this is, sorry, the port is, of course. Okay, now I need to turn off the Delph and then hit the curl. Then it's escaped. As you can see, Delph is not the perfect, so it hangs sometimes. And then you need to hit the URL with the curl and hits the server, then notice that the Delph is not working, and then he quits. But I will recap all that stuff at the very end. Okay, so let's run this Docker. And now let's try to attach to this to this Docker. Yeah, so I can show you also the configuration for that. Remote and Docker is here. So that's the part, okay? And the very important thing is that we need to pass the exactly directory by hand, because we cannot reuse this workspace root because it's a different path inside the container. So we need to pass the information inside the container. Where is the application? What's the main.go file? Just to make it possible to debug it, okay? And so let's run it, okay? Let's remote and Docker. We can run the applications and we can hit the curl and we are there, okay? So pretty important thing is that this, we need to pass this extra flag, okay? To make the whole debugging in Go possible. And I guess that's it about the debugging. So, let's, I'm sorry, there's also one more thing about the debugging. Debugging also has some extra thing which is called post-mortem. It's not very common, but you can also analyze the core file of the applications which will be printed when the application dies, okay? So sometimes application dies, we don't know why, it's too late for debugging, but we can check something with the debugger itself, okay? So we can get these core files and we can dump the core files when the application exits and crash somehow, okay? And this core file contains a memory dump of running process, okay? So how we can do that? We need to set extra flag, which is called go traceback, set to crash, then run our application, and then, for example, send a kill. And then we'll have the core dump printed in the, by default somewhere in the directory, I guess the local one. And also we can use the G-core to make the core file directly from the running application. And then we can run the core delf and say delf core and pass this application, but also pass the binary file just to be, just the debugger needs to understand what to debug and how the structure of the application looks like, okay? So with such thing, we can see the heap dump, the memory, also the allocations of some variables, but of course we cannot set the breakpoints and so on, okay? So that's how it works in this post-mortem debugging. So let's recap the whole debugging. So debugging in Go applications is very easy when we are running everything on a local host. And attaching to production application, which are not non-Docker, is also pretty straightforward, but we need to remember about two things, that it stops the execution of the entire app when we start delf, okay? So when we start delf, we cannot operate with this application, okay? We need to we need to set the breakpoint and then the application can operate and works, okay? And also we need to have these proper binaries built with extra flags, and every single time when we escape and kills the session with the from the Visual Studio Code or any other ID debugging session, then we need to restart the server, which is also annoying, okay? And in container, it's also problematic because of two things. That first of all is that we need to run container with unsecure way with this extra flags of security, and the second one is that we need to create a dedicated container image with the delf itself there, okay? It's also not very very nice. So those are the problems. And even if our application dies, it's not too late for debugging. You can use these core files, okay? Let's now talk about the profiling. Profiling is, I guess, more fun. So what's profiling? Profiling is just a tool to analyze the complexity and the cost of Go programs. So we can analyze, for example, how many and where our application spends most of its time, and where are the expensive, for example, calls, and what functions are very expensive when it comes to the memory or CPU. Okay, so so there is also a built-in tool in Go which is called pprof, and this tool is allows us to visualize those profiling and the profiling data, and we can profile the CPU, the heap, and also more things like block profiles and thread create and Go routine and mutex, and everything, as I said, is built in, and also you can use it also in a code. Okay, so let's have a look how we can run this profiling in Go. Okay, so the very first thing is through the benchmark. So we can run a benchmark, which is just testing one particular function, and we can set some extra flags like CPU profile or mem profile, and then our profiling data would be automatically generated from this running this benchmark. Okay, I will show you the example in a minute. We can use this blank import, also a pretty nice thing. I would say even neat, and I'll show the details in a moment. And of course, we can, for a short-lived like applications, for example, CLI, we can also run this profiling and collect the profiling data also from the code. Yeah, so we can say, okay, start and then stop profiling for some time. Okay, so let's start with profiling with the import. Okay, so the only thing we've got a already server, HTTP server, which is running in Go. We need to add this blank import. Okay, and this blank import by default will add extra handlers, HTTP handlers, to our application, which will which allows us to run and to grab the profiling data from the server. Okay, so it's really nice. Google does that, for example, for in every single production server. They've got also this profiling run, of course, on the different port for the security reasons, and then they are generally constantly checking this profiling data. So they are, for example, in every hour they are just collecting the profiling data and storing them somewhere in the storage. And if some problems were appealed, then they are getting and trying to fetch the data and run the pprof, and then analyze what was happened. Okay, so they are doing that constantly, just to make them even the data and the situations from the past. Just they can analyze them even later on. Okay, so let's check this example. In this example, we are of course setting and putting the blank import at the top, and we have two extra endpoints. Okay, stats hello and hello. Okay, the very first one is it has wrapper, so it's like a middleware in Go. So you wrap your handler, and then you run your code, this hello handler, which is just basically printing the hello word, and they are adding some extra functionality to this handler. Okay, and the stats are just printing the informations about the IP and the session, for example, from what was the user agent and from which browser we hit this page. Okay, so if we have this import, I guess I might covered most of the fact, but it's very powerful but also dangerous. So don't do that on the production on the same server, I would say, because if so, then anyone from the world or anyone from the existing world can hit your endpoints with the profiling and then collect the data or stop execution even, and just to make a DDoS or also profiling degrades the performance. So there is plenty of security holes there. So usually you're running two servers inside the application. The first one is just run on the different port, and the another is just handling all the requests from other applications or end users, and the very first one is just secured by some security group, or it's not exposed in the Kubernetes or Docker or any other stuff. Okay, so there's plenty of ways how to secure this, but of course we need to remember that. Okay, so here's the example how we can do that. We are running in the new Go routine, so it's like another server, and we are serving all the critical and p-profiling on the different port than the main one. Yeah, so the p-prof is run on this port 1337, which is here, and the business logic of our application is run on a different one, and usually you are exposing just the second one. Yeah, this one like 8080 or something. Okay, so let's have a look how to play with this pprof. Okay, so first of all, we need to make this profiling. So the first thing is just to run the application. The pprof endpoint is exposed, and then we need to, from our terminal or from any other place which is also possible to make this request, we can hit this with go tool pprof, and then we are passing the arguments -seconds, so for how many seconds we are going to collect the data, and then run this, and it's going to download the data and run this pprof tool automatically. Okay. Then, of course, we can have two ways of playing with the pprof. One is the web one, and then there's also the terminal without this -HTTP flag. Okay, and also we can even have a situation when we run the pprof at some point, and then after some time we are running it again just to check whether it's better or not, and then we can compare it, and then we'll see whether our improvements in performance of our applications are good or not. Okay. So let's go to the demo, okay? So so here we've got our applications. So let's first run it. Okay, so now we have this 8090 server, and now let's try to check what is going on here. Okay, so if we hit this curl, we see that we are collecting extra informations. So the very first one is just information that from that stats hello endpoint was run on my host name, which is Mateusz MacBook Pro, and no OS, no browser. So the user agent was not able to parse it, and because of that, we are setting that the value to 1. Okay, so there are some defaults, so we are setting that to 1, and also we are calculating the how many of the microseconds took the whole handler to run the business logic. Okay, so I run these applications with this --print stats flag just to show you that we are collecting those informations. But to show you the real performance of our applications, let's run it without that. Okay, so now we have applications, and instead of curl just hitting the endpoint stats hello, let's check how many requests we can handle, and what would be the average of our web server. Okay, so I use the tool which is called Hey. So now I can say, okay, run our application, attack our applications with this Hey tool for 10 seconds and send as many requests as possible to the endpoint /hello. Okay, this is the one which is fastest, which is not collecting the data. Okay, and not collecting those extra, information about the host name and so on. Okay, so it will took 10 seconds. Okay, now we see the result. Okay, here is information that we are able to handle more than 46K of requests per second. Okay, with our hello world endpoint. Okay, so let's now run the another one, the one with this stats hello. Okay, so just to check what's the difference between the one which is also collecting this extra information about the user agent and the one which is just plain returning the hello world text. Okay, so let's run it for 10 seconds. Okay, come on. Okay, now we see that we've got 40K. Okay, so we are slower by 6,000 requests. Okay, so now let's try to use the pprof tool and analyze where our time is spent and how to improve our stats handler to make it faster. Okay, so to do that, we need to run our applications again and collect the pprof data. So by default, we can check what's this under this this endpoint, even in the web browser, without this pprof tool, because it's pretty nice. So what's there? We are now not collecting the profile in the real time, but now we are just checking what information we can get by default without running the pprof from the debugging endpoints which are available here because of this blank import. Okay, so here what is really important is, for example, heap. So here we can see all the Go routines, and all the heaps from the Go routines, which are not very important in that state, but at the very end they are really nice information and really interesting, I would say. For example, we can see the pause NS. Okay, so pause NS are nothing else than the time which was spent on the GC. Okay, so now we can have a look at this array and check whether our GC is performing well or not, and how much of the time was spent on the GC. Here are also information about the how many times was GC run. So if I refresh this page, we can see that, let's go, it's still 800, but if I run any other traffic on our server, let's check it again, and now we can see it's 968. So the GC, if it's not needed, then it's not working, but if there is a traffic to our server, then this GC is increasing. Okay, now it's more than 1000. Okay, so we can have a look at some memory data from this heap. We can have a look at the number of Go routines, what they are currently doing in our applications. We can check where are the allocations, and so on and so forth. Okay, so that's pretty nice, but it's not very, I guess with this endpoint, by default, we cannot check why our endpoint with the stats is pretty slow, and we should use the pprof just to download and analyze the data, okay? So let's do that. So to do that, we need to first attack our server with some traffic, and in the meantime, run the pprof, okay? So let's do that, and now let's start the pprof, which is now collecting the data for 5 seconds. So it's going to check what is going on for this time. Okay, so it's terminal version, the first one, which I'm going to show you. So what's nice is that usually we can say, we can write top. Top is a really nice function in pprof, which will just write 10 places where our CPU was used for and was spent most of its time there, okay? It's nothing interested there from our perspective, because those are mostly syscall and some runtime things, but there is nothing which we write, yeah? So it's not our code, okay? So I guess we need to improve it, and so we can type top 25, and now we can see something really interesting. And because now we can see that there is my function, which was not this one, but this one, okay? So we can see that there is a with stats, okay? And this function was written by me, and we spent 5 seconds, so a lot, there. So this is a first place where we need to have a look, okay? And there is also another extra flag, which is called come, which is going to say, which is going to collect not only the single place where the time was spent, but also all the functions which are called by this particular place, okay? So now if I'll call this minus cumulative, then my function, this with stats, is going to be on the third place. So definitely this is a place where we need to have a look. But before that, let's exit that, and let's show another way of showing that, and let's run it on port 1891, for example. Okay, so again, we are generating some traffic and then getting the pprof data. Okay, 5 seconds, we are collecting the data, and then immediately we'll have a UI, which is open, and this tool is built in the Go, so this is nothing which you need to install by yourself. So why it's nice is that it shows you the tree where your application spent most of the time, and you can see that this is a finishing request, so it's like closing connection and sending the data to the wire. Nothing really interested from our perspective, because usually you are using the by default HTTP server from Go, so it's not like, you know, really smart heads are working to make it fast. Here is the same, which is just reading the request. But here in the middle, there is a server handler, and this is something which was created by us, okay? Especially that handler func, the handler function which I've already wrote, okay? And here is with stats, and with stats is definitely something which I wrote. And here we can see that we spent almost 5 seconds there, yeah? And then we can have a look that this function called another function get_stat_stacks. And this function spends like 4.84 seconds there. But in fact, the most of its time was spent in here, yeah? Handlers get_stat_stacks. And another, even not in this particular function, but calling the os.hostname. So anyone knows why os hostname is so expensive? Okay, if not, then I can tell you that it's under the hood is making the syscall to the kernel, checking what's the hostname, okay? And that's why it's so slow. So let's try to analyze it in a different view, okay? So this is a tree view, but there's also, a flame graph. And this is like neat. So previously it was written by Uber. So Uber has its own implementing of this flame graph, but now it's integrated and merged into the pprof tool built in Go. Okay, so here we can see what we can see. We can see that this is a read requesting. This is a finishing requesting, still nothing which we can improve. But here is the serving. And here we can see that there is os hostname. Just to be sure, what does it mean? The wider block is, the most of the time of our CPU is spent there, okay? So we are looking for some wide blocks, okay? And here we can see that os hostname is like 25% of the whole execution of our application, so a lot. So we need to improve that. We'll do that in a second, but also what is important and worth to notice is that the colors means nothing, okay? So don't think that whether if it's almost red or orange, then it's worse than yellow or almost yellow, okay? So it does nothing. So colors are just to make some difference between the blocks, okay? And it's called flame graph, and it's pretty common even in the different languages like JavaScript or even Java. So let's try to analyze this host name. Yeah. So here we can see that after I call the host name, there are only syscalls and nothing very important. So let's try to go to the code and try to make it faster. Okay. So so there was a with stats. Okay. And with stats is calling this get_stat_stacks, and this is our a place where we need to have a look. And what it does when we are sending the request, it gets the request, and then we are collecting the user browser, the user OS, and also the endpoint, which is accessed from the external, and then we are collecting this OS hostname. But the truth is that I don't need to check this hostname every single time, because it doesn't change very often. Yeah, I would even say that usually we don't change it in the meantime. Okay, so what we can do, we can remove it and set it to some global variable. Yeah, let's call it host, and we can say that it's going to be string, and let's call a function which we'll create in a second. Let's call it hostname. Okay. And now we can say that the hostname is going to return a string, and we will check this OS hostname and make the syscall, but only once. So we'll set it to the global variable, which is going to be only called once, okay, at the very beginning of our application. So we can say that, okay, if the error is equals nil, then we can return it, so we can return host. But otherwise, if somehow syscall was broken and there are some errors, then we can just return unknown. Okay, and then here we need to add this extra information. Yeah, so instead of setting it every single time, we can say use host. Okay, it should be reformatted automatically, and okay. So let's check whether we are improving or not. Okay. So let's stop the ppref analysis, let's stop our server, let's run our server once again, and let's run our applications now without the profiling, okay? Let's have a look in the hey tool, which is just attacking our server, whether we are improving or not, whether we are faster than 40K, okay? Let's have a look. Now we are not very much, I would say. It's 41.5K requests per second. But I can even run it once again, because I guess we should do it better. It's not much, 1,500. So let's try again. again, 41, not much. But let's check how our flame graph will look like in the pprof after our improvement, okay? So we are attacking our server one more time, and we are collecting the profiling data one more time again. Okay, let's do that. Okay, and we can see that, let's go to the flame graph. And now you can see that we've got the request finisher, which took most of the time, a request reader, which took another lots of time. And now there's also the runtime stuff, which are not very, there's also not the place where we can improve. But here we can see that this is also not our handler, but here, I guess, where is that? I guess maybe it's on the left. Yeah, it's there. Okay, so you can see that I improved a lot, because previously it took like one, I don't know, it was like a 20% or 25% of the whole invocation. Now it's just like 5%, so it's extremely fast. And now we can see that there is with stats, yeah? And of course we can have a look and try to parse this user agent and make it faster. Of course we can make some further analysis, but to be honest, I'm not going to show you, but I hopefully in this example you can show how easily with the flame graph and pprof tool you can find a bottleneck, find a place where your CPU spends most of its time, and make your whole application faster. Okay, so let's get back to the presentation. Okay, so we can also do the profiling and generating the profiling data from the test or a benchmark. Okay, so how to do that? We can have a function, for example, which is calculating the Fibonacci. Then we might write a benchmark. In Go, benchmark you're writing just by adding the benchmark at the very beginning in a test file, and then running in some time. Okay, for some time, usually you're doing that in the for loop, and the n needs to be smaller than b.n, which is the number which is generated by Go, and it's going to be like 1, 10, 100, 1000, and so on, until for some time. So benchmark is usually run for like few seconds. Okay, so that's how the benchmark are created in a Go, and then what is really important is just when you're writing this this benchmark, you need to pass this extra minus bench just to run the benchmark, only benchmarks from the test file, and then add this CPU profile information, which will just creates the CPU profiling, and then you need to, of course, run our tool, which is called pprof, and then pass this profiling file. Okay, and then it's going to open your web browser or terminal version of pprof just to analyze what's going on. Okay, and really nice also the mem profiler. I'm not going to show you, but it's really nice because it also shows you the place where your function allocates like most of the memory. Okay, and also you can run a benchmark and pass extra flag that show mem, and then you will see how many allocations your function does. Okay, it's really killer feature if you would like to have a fast hot path usually in your applications, because if something is not allocating much, then GC is not run. Sometimes like it's run only sometimes, not very often, so it's really good for a performance of your application. So usually you are not only profiling the CPU data but also the memory data, just to find out the allocations and get rid of them, because there are some techniques in Go how to do that. Okay, the manual way how we can collect the profiling data, we can just create the files. So like pprof mem, pprof CPU, of course, close them at the very end. Defer does just call these functions when this function is going to be closed. Okay, so defer will just move the CPU file at the very end of this function, and then we can start CPU profiling. For example, run some leaky functions, wait some time just to collect the data, and write heap profile and start CPU profile. Okay, that's it. That's how we can do that in the manual way. And let's have some recap about the profiling. Okay, so I'd say that Golang creators and maintainers did a great job with profiling. It's really, really nice and convenient way to find and optimize your code. Okay, and the blank import is very important, but it's very nice but dangerous, and it makes your applications insecure. And please write and expose the debug information on different ports. Okay, and if you will, with the flame graph, if you will see what's your problem and where your application spends most of its time, then please write a benchmark just to test this particular function. And this is the easiest way to find out the bottlenecks and improve the speed of your application. So not collecting the data and run like end-to-end tests, but just to isolate the problem and then try to fix it. And of course, you use flame graph. This is the easiest way to find out. And I guess the visualization is pretty nice. And of course, web-based pprof is better than the terminal one. And please don't prematurely optimize, of course, as always, and as in every single presentation about the profiling and making your application faster. Okay, so now let's talk about the tracing. So tracing is nice, and tracing in a Go, it's also extra tool which is built in. It's called Go Tool Trace, and it allows you to capture some really nice events from your system. And those events are, I would say, really nice, but it's not like that if you try to find out the best way to make your application faster is just to start with trace. Start with usually with the pprof and try to use different kind of problems with the tracing and goal tracing. Okay, for example, the GC or kind of locks which might be blocked your Go routines. But let's see. Okay, so trace, Go Tool Trace is just a tool for visualization as pprof, and also it's really powerful. It's also built in, and you can have a view at this trace. So we'll see that in a minute in the demo, that you can have a look and analyze the tracing data with that. You can make the Go routine analysis, how many of them is, what they are doing, what the syscalls are inside the Go routines, really low-level stuff. Also the network and the sys and syscalls as well, and the scheduler things. So this is pretty nice when you would like to have a and just get the knowledge why your Go routine waits for another, or whether under the hood in the runtime some for example Go routine is waiting for something which is not happening. Okay, and there's some kind of starvation. Okay, so of course it's the same package, and we don't need to add any extra thing in our server just to collect the tracing data. But what problems we can solve with that? So latency problems, poor parallelism. So if we've got, for example, worker pattern, and we have like tons of workers, and now we can notice with this tool that, for example, half of the workers are in the idle state and they are just waiting for something and it's not happening. And we can do that better way. Okay, and also log contention. We can also track that with this tool. Okay, so when the Go tool trace is not appropriate, so when we would like to have a knowledge which function is slow, then use the pprof. For example, when we would like to know which function spent and uses CPU a lot, also is not the best tool, then use the pprof. Okay, so how we can start with tracing, how we can collect the data, almost the same way as a pprof. Okay, so with the benchmark minus trace flag, blank import as I mentioned, and also we can do that by hand by calling trace.start inside our Go program. Okay, so let's go with this tests and benchmarks. Again, example with the Fibonacci benchmark, nothing changed comparing to the pprof, but running this test, we need to add extra flag, not minus profile, but minus trace. Okay, and then collecting the data, and then just analyze this trace. Okay, with the import, same stuff, exactly same thing, and we can see and have a look that this is a blank import. Of course, how to do that? We need to. The difference is that now that we, with the Go trace tool trace, we don't automatically fetch this data, but we need to first download it and then run tool trace just to get it and analyze it. Okay, so like it's not the one step, just we need to only run this Go tool like with the pprof, that we are running pprof and he's going to download that and analyze, but first we need to download it and then start this tool. Okay, and there is only web-based, so there is no this terminal one. And the manual way, as you can imagine, we need to create a file, close it at the end, and start the tracing, and then trace stop, call it at the very end. So really almost exact same thing like with the pprof. So let's have a demo of that. Okay. So now we've got application, and our application is again. So we can maybe not spoil. So let's go run our main application. Okay, without any stats. Again, our port is busy. Okay, turn it off. Turn it off. Okay. Run it again. Now we've got application, and now we can have a look with the curl what it does. Okay, so only the pprof stuff. Hello. Okay, and we see that we've got some information that our endpoint was visited n times. Okay, so that's the difference here. And now let's have a look what performance we can get from this particular endpoint. Okay, so let's run again this hey tool for 10 seconds, and let's sorry, it's hello world. So let's run it for 10 seconds. Let's see how many requests per second we can get. Let's check it. 83. As we can see, we are, it's like heavy operation this time. So let's try to analyze that with the our trace tool. Okay. So again, exactly same situation. Now I need to run the workload, run and attack our server. In the meantime, I will download the data and then run pprof to analyze that. Okay. So now I'm attacking the server. Now I'm downloading the data. Okay, and now I can set go tool trace set one.trace. Okay, let's run it. Let's make it bigger. Now we can have some functions which we can have a look. We can check what's the go routine analysis. We can have view the trace itself, and also we can have a look at some kind of scheduler latency profiles. Why it's important? Because Golang is not using the threads from the OS, but it's using the threads from the OS, but it has another scheduler which is on top of that, and then is going to operate on the Go routines. Yeah, so the Go routines is run on this thread from the OS, but it has like another scheduler. So it's not using the system scheduler, but it uses the system scheduler, but just to get the thread from the OS, but then is going to also run its Go routines on this particular with its own scheduler. Okay, but let's start with this view trace. Okay, and let's analyze that. So now we can see that we've got something, and what is really nice here, or what is not, is that we've got only one processor, but the fact is that my application, my computer has like 8 cores, or 4 cores and like 8, but it should shown it like 8 things. So now we can see that like 7 other cores are in the idle mode. Okay, why is that? Maybe some Go experts which can answer that. No, because there is some extra environment variable in Go, which is called GoMaxPros, and with that extra variable, we can limit the number of processors and the cores which are used by the Go program. Okay, so with that, I limited that to 1. And because of that, we can see that only one processor was doing anything, and the rest was not even touched by our Go program. Okay, so that kind of problems you can solve with this tracing tool. Okay, so for example, poor parallelism, not used all the cores. Some cores might be in the idle modes, and also the gaps which are because of the waiting. But let's improve it. Okay, let's set it to 9. Run our application. Go run main.go again. Okay. Now let's attack our server one more time, and let's call this curl and download it to trace number 2. Okay. And then go tool trace but the 2. Let's run it. Okay. Now let's view the trace, and we can see that it's much better. Now we are using 4. But only 4, not 8. Okay, still we can see that the numbers are not very good. So I guess if I'll have only 4 calls, it should be 3, but it's 5. So it means that I get 8. If I get 8, then why the rest is not doing anything? Okay, so the truth is that some Dambas sets in this data main go sleep, and because of this sleep, we are waiting, and the fact is how the Golang scheduler is working is that there was not that amount of work which can be splitted into 8 cores. So there was only work for 4. Okay, so if we'll remove it and try it and run it one more time, okay, then attack our server, then collect the trace with number 3. Okay, then call this tool but analyze the trace number 3. Then we can see that it took lots of time by splitting. Why is that? And now we can analyze the trace, but not everything in once, but we need to split it into 3. And the truth is that pprof is just getting the snapshot of our system in with some time. Yeah. So for example, every single 10 milliseconds we are making snapshot, and the data and the number and the amount of data for example the pprof is pretty small, but in the trace we are collecting all the events. Okay. So every single invocation, syscall, anything is dumped to the file. Okay. And because of that, our trace data is huge. Okay. So let's try to analyze whether all our cores were utilized. Okay. And we can see that yes, okay, from 0 to 7 it's 8. Okay, so now we can see that our program was utilizing the CPU almost at max. Okay, there are still some things which we might analyze with this tool. If we'll try to dig in very deeply, we can, for example, have a look exactly in every single syscall, every single function invocation in Go, and have a look what was going on there. Let's try to click it, and then we can see what's the wall duration, when it was started, and what was doing, and so on and so forth. So it's like really low level, very interesting stuff, especially when you would like to track the poor parallelism. Okay, when you would like to track that not every single CPU is used, and it's like plenty of low level stuff which you can find with this trace tool, especially when you have a log contention, for example, and there are multiple Go routines which are waiting for on the for example mutex. So that kind of problems you can solve with this trace. Okay, and let's recap the whole presentations. So we start from the debugger, and then it's the truth that Delph is still missing some features. I would say that Delph should be built in the Go, and I would say that this as a pprof, as a tracing, also the debugger should be built in and just maintained by the core Golang people. And with that, for example, feature like you know, continuing the application when we start the server should be like built in, and the hanging problems, there are plenty of some missing stuff in the Delph debugger that should be improved, and the work is done and lots of improvements are there, but still some are missing. Yeah, so I guess maybe there will be some kind of movement that they're going to somehow take it from the Derek Parker, which is a great guy, and he built it, and just to make it a built-in debugger. Okay, then debugging Dockerized applications is a bit problematic. So remember about this insecure running and that stuff. And also please remember that even if your application died, it's still not that late, and you can still debug some and check the memory. And about the profiling. So profiling is really easy. I would highly recommend to everyone that. And please remember that this blank import is powerful but problematic, so hide it. especially on the production servers. And usually, if you will, with the flame graph, of course, you will find out which function is slow, then use and write a benchmark just to analyze and find out and make it really, really fast and improve it with the benchmark. It's the easiest way. And of course, if you have problems with the logs, GC, poor parallelism, use the tracer tool. It's really cool. And thank you. That's it.
Unfortunately, we don't have any time for questions, so if you would like to ask Mateusz anything, please join him on stage or in the lobby. Thank you.
Thank you.
Zaraz pójdę tam do
Tak.
chłopaków i...
Raz, raz. O.
Hello everybody after the coffee break. I hope you are doing fine. For those who haven't been yet at stage 9, I would like to start with some rules. First of all, please turn off your phones or put it in silent mode. Secondly, if it's possible, please don't leave the room during the lecture. And if you will have a question to Dmitry, I will be standing near the exit in the question section. Our next speaker, Dmitry Trukhanov, is living in Wrocław for 1.5 years. He's attending Toastmasters meeting to become a better speaker and also trying to improve everything around him. Please welcome on stage Dmitry Trukhanov with his speech, Black Box Performance Analysis.
Thanks everyone to join me today, because it's quite late already and last session is always quite hard in conferences. Black box performance analysis. I'm doing it a lot. I'm working in Luxoft as a performance engineer. That's what my position states. I'm doing a lot of stuff, and black box performance analysis is one of the biggest things what I'm doing. What I understand under black box performance analysis? Hey, no? Oh, strange, very strange. It's very simple. On the first glance, it's very, very simple. You're taking your program which you have developed, you're giving it to user do something with your program, you're getting metrics from your program and from operating system, of course, and you're looking at what is going on. And the next question, which for some reason no, maybe this way. Why on the earth do we need another type of tests? We have cut coverage. We have linters in the first place, which are telling us all the problems with our code. No? We having continuous integration, continuous delivery. We're having fuzzy testing, other testing, a lot of testing. And now coming me saying, oh guys, let's do another testing. And this test is quite time consuming. Why should we do such a thing as black box performance analysis or black box analysis at all? No. I want to ask you very simple question. Who could try to interpret what is displayed here? Hand, please. Someone? What? It's a chart. It's a chart of metrics. But what could we say about this chart? What could it show us? Is it good program? Is it bad program? Who? Memory leak, yes? Memory leak, it's most obvious thing, of course. But no, it's not memory leak. It's another type of leak. And these types of leaks could be met very rare, but could be met really in experience. It's analysis of one program which quite standard for testing. I will not name it because of NDA, of course, but it's quite a standard for QAs, QA teams. And what it shows here is I/O operations leakage. What it shows here is that program, after each run of some operation, starts to consuming more and more input and output operations. What? How it is possible? It's not something that this program is trying to read something continuously. It's not something like this program is working hardly with file system. No, this program what only does is just an automation for just regular programs. So user clicks play, it plays some scenario and closes this automation execution. And it stays to consuming more and more input and output operations. Why? These guys have said me that it's not possible because why? We have tested our program quite good. Why? And I have said, sorry guys, we have real situation. I have not seen your code. I have not seen your approaches to code. I have not seen your approaches to testing. I have not seen your programmers at all. But I see your program. At the end of the day, it do very strange. Some very strange thing, like I/O leakage. It sounds crazy to my ear, actually. The other thing which I have seen, it was absolutely the same chart, like displayed here, but the only difference, it was CPU leakage. User was pressing in browser one button, and browser started to consume additional CPU. He pressed this button once again, just to repeat our operation, not to start some new operation. And CPU started to consume, program started to consume more and more CPU. CPU leakage. Have you ever heard about this? Me personally, no, because it sounds crazy once again. What else? It could be other crazy situations. Let's return to more common situations. Memory leaks. Memory leaks is all over the place. I know this conference is mostly for C++ developers, and C++ developers can see memory leaks quite often. But also, I'm working with programs written in C#, in Java, and I'm coming to guys showing absolutely the same chart and saying, "Oh, hello guys, your program is leaking," and they're starting. Wait. Our program is written in C#. It works on .NET. We have managed memory. Do you know what managed memory is? I'm saying, yes, of course I know. You think that memory leaks is not possible there? And they say, no, garbage collections do all the thing. And I'm saying, oh guys, sorry, but I have captured it for 24 hours. 24 hours is not enough for your garbage collection. And they've started, you know, maybe your environment was not so good. Maybe you have set up garbage collection somehow not to work well. And because of that, we even have changed name of this. We do not call it memory leak anymore. We call it unreclaimed memory allocation, because some of the guys telling to us, it's not memory leak. I've just cached all the objects which I have received. And I've said, really? I'm just loading the same settings 10 times in a row and you caching it every time? And they've said, yes. Okay, it could be, maybe it's very different. Memory could be the same. What else? It could be handles. A lot of programmers, a lot of developers, I'm from Windows world, so I will be talking about handles. In Unix world, you could leak descriptors, of course. Handles. Programmers just creating some objects, they may be not cleaning it because it's really cached in this case, and they're creating more and more handles to the same object. And operating system is have very big tolerance to such situations. So you could allocate thousands of handles, 10,000 of handles, hundreds of thousands of handles. But anyway, in some point, operating system will start choking. It will start giving you some stretch errors. It will produce some nasty errors and event logs in your logs in its Unix and so on. So everyone should remember not to allocate, and without really looking at your program as a black box. Not so many developers are able to see that they're linking the same objects many times in loops or something like that. What else could be leaking? Another very nasty situation is leakage of threads. Developers are allocating threads just to connect in asynchronous mode. Some servers trying to do some asynchronous job in background, and this is actually was the case with this program which I'm displaying here. So IOPS were leaking because they have allocated additional thread for each run, which was trying to read some configuration from the disk. So actually IOPS were increasing, but it was not reading actually not a single byte, because file which it was trying to read was not existing on file system. Crazy. What else could be? A lot of things. A lot of things. And actually, it could be very hard to determine these leakages during your development stages. It could be very hard to detect such leakages during testing stages, because what you are really testing during your testings, you're testing user acceptance. You're looking that everything works fine. You're looking that no logs are not displaying some strange operations. You're collecting your own metrics from your own application. So you're not trying to understand, not you, maybe some nasty developers, not trying to understand what is going in general, what impact your program having, what impact your program having on operating system itself. Because you maybe, or nasty developers once again, maybe not interested in operating system, because we all know that memory is cheap in our era. So why should we analyze it? But this could lead to some very nasty situations. And what I really propose to do with all these situations. Returning to the beginning of my presentation, I suggest to do black box performance analysis. I suggest to everyone not to just look at your program which you have developed, not to look at some near systems which you are interacting with, for example, databases, for example, web servers, but look at operating systems in general as well. No, not working. So what do we need to do black box performance analysis? Very simple. We need to collect metrics, operating system metrics for in the first place. In Windows world, you could do it very simple with performance monitor, which is built in any version of operating system. It could be server, it could be client, it could be anything. In Linux world, you need to do some additional steps. Metrics itself provided by operating system, but to collect it, you need to have some additional system like Zabbix, Nagios, maybe some fancy time series database. And you need to collect it and analyze. But it sounds very simple. But what could really go wrong with collecting? A lot of things could be very bad, go very bad with your collection of metrics. For example, baseline. I have seen some guys trying to, and you should see this actually in internet all around the world. Database comparison, PostgreSQL versus MongoDB, something like that. People are comparing something which is incomparable. To do proper baseline, proper black box analysis, I suggest everyone to compare with something comparable. And under comparable, I understand baseline. What is baseline? Mostly it's one of two things. Previous version of your application, if you are 100% sure that your application is already running quite good. So it's not having any bad impact on operating system, on end user experience, on your servers and bills on Amazon maybe. And the second thing, you could compare your application with no application. For example, you have just developed a new Chrome extension. And it's very simple. To what could we compare your Chrome extension? Of course, to plain vanilla Chrome. Just capture some Chrome data, look at how it behaves in your environment, and compare it with your extension which you have developed. Test plan. I have seen also people comparing something not really comparable. They have, for example, in one browser have opened a Google start page, and on the other web tab they have opened some pudelek.pl, don't know. And it's very different. They're seeing, oh, really? My application, which I have running inside of Chrome extension, is consuming more memory just because I have comparing Google to some very big website. Test plan is very important. You need to compare, you need to reproduce test steps one by one in each environment, in your baseline and in your program. You need to implement in this test plan the most common operations which users will be doing with your application. If your application providing, for example, collecting of some system metrics to send it further to you when it will be crashing or something like that, and you use this operation like twice a year, there is no point actually to understand what impact it has on your operating system, on end user, on your servers. Test the most common user applications. Time intervals also. It's very important to do all the tests with predefined test interval, time intervals. For example, you may be doing some HTTP queries to some server. And in one case, you are doing HTTP queries once an hour, and the other is once per 2 hours. Your web server could have different caching settings. In one case, you could see, or you could hit cache version. In other case, you could hit online version, and we'll see very, very different behavior on your application. So time intervals should be also predefined. Cooldown. Returning to these guys who are saying that in managed environment we do not have any memory leaks, we have only caching, we need to do cooldowns after each testing. For example, you have done some testing of your application, run user load, or maybe not user, it could be done on server as well, done some operations, and please wait for at least 30 minutes after it and see how operating system is behaving. Also, cooldown is very important for operating system itself. For example, when you're starting in one environment, your application, it could be checked by antiviruses, DLP agents, a lot of stuff could be going on. And after closing your applications as well, sometimes you have allocated some memory and it was freed up. But sometimes when you have run your applications, consumed some memory, and closed even your applications, memory is not freed up. If you have allocated memory in system pools, if you have allocated memory in Windows, memory windows, I mean, of course. You need to have test plan with predefined time intervals and cooldowns. And in baseline and in your application testing environment, it could be similar. The second, the fifth thing, you need to use the similar tools in each environment. I have seen in my experience that some people were running, because to tell you the truth, who will run, for example, 24 hours capture and 24 hours running of applications manually? Of course, no one. Maybe some. We will use some automations. There are a lot of things all around the place. We could write something ourselves. We could implement something in auto IT, auto hotkey. We could implement something in Perl, even, do not know. A lot of apps watch one of the system, Tricentis Tosk, as I remember, a very big system to automate this. And all these system, all these applications, all these tools having their own impact on operating system. Once we have almost failed product from our developers, inner developers, because of memory leaks in operating system. But further analysis showed us that it was our automation who really introduced these memory leaks into Outlook. So Outlook, automated through this way, was leaking more memory than automated other way. And we said, oh, yes. So your test plan with predefined time intervals and predefined two cooldowns should be executed by the same tools in your baseline and in your testing environment. And the very last thing, but not least, is environment itself. We know that Java is running on 3 billion of devices. We could test our application, for example, on on some smartphone or on some Linux or on some Windows, and would it be really comparable if we compare memory consumed on Windows, Android, and Linux? Of course, no. And this is quite radical comparison, but less radical is comparing different versions of libraries. For example, you're running your applications on the same operating system with the same predefined application set, but one library have different version from other environment. And could you really say that memory leak introduced by some application in operating system is really caused by your applications in this case, or by this library which have introduced some problems? To sum up, to do all this black box analysis, we need to follow quite simple things. We need to collect metrics, but we need to collect them in quite predefined and quite strict way. So we need to do each time baseline analysis. We need to prepare quite a good predefined test plan. We need to have predefined time intervals in both environment and baseline in our test environment. We need to introduce cooldowns to be sure that if we have some garbage collection, once again, if we have some operating system procedures which are cleaning something, if we're having some predefined tasks which are doing some job for us, we need to understand if they're affecting our applications or not. We need to use identical tools in each environment. And of course, we need to have identical environment in our baseline and in our test. And this is actually what I wanted to tell you today. And I wanted to encourage you to do black box analysis in your environment. And now it's question sessions.
If you have any questions, please join me here.
No one will be doing black box analysis, no? These guys who provided me with this chart were good programmers as well. Their program were doing very clever stuff. It was written quite good. They just forgot quite small line in their code which was not visible by statistical analysis, or not visible by linters, were not visible by cut coverage and unit tests and so on. So even if you are good programmers, it's very good to double check yourself, because it will give you better understanding how your program behave. For example, you will be seeing in which areas of operating system you're allocating memory, which drives you're writing to. Maybe in test environment which you are doing, you will have too big input-output delays, service time or transfer per second in Windows. It could be quite a lot of problems, and to make a step further to solve it, black box performance analysis or black box analysis is one of the tools could really help you.
Okay, I have a question. Do you have an idea of how would you integrate this into an automated continuous integration pipeline? Like, running is one thing, and you could always probably generate some kind of report, but are there ways that you can automatically like pass or fade a specific version, or does it always require a manual review of the reports? Yeah, are there ways to automate this?
Great question, thank you. There are a lot of possibilities for automation, but to tell the truth, full automation of this process, in my opinion, is hardly possible. You could automate collection of metrics. You could automate your test plan. You could automate deployment of your environment, of your time intervals, of your cooldowns. But really interpret what is on the chart is a job for engineer. It's job for specialist who could really tell you what is going on and why it could be going on there. Because like on this chart, we could do maybe some, how it's called, anomaly analysis for this. But to tell, but if you will have seen this in previous version, anomaly analysis will not do anything in your case as well. So to include in CI/CD, it's always possible. But interpret results, it's to a human for now. Maybe machine learning will be replacing us soon, but code will be automated as well in this case. So none of us will be needed in this case.
Yes, hello. Thank you for your great talk. And I have a question. So I work in a field where it is not a big stretch of imagination that we are the owners of the one and only product of its kind. And it might be a very basic question, but in this case, what would you select as the baseline? So we have one of a kind application and we want to find a baseline for our black box testing.
Thank you for your question. As I have said before, if you are 100% sure that your application is running quite good, at least one version, you could select your production version as a baseline. You could test it on your own and without comparison. for example. You could compare your production version to not having your application on environment, and then use this application, production application, as a baseline, and then compare your new developed versions to this already deployed production version. This is what we are doing, at least. Thank you. More question?
I don't see anyone anymore, so thank you.
Here we have one.
Okay, please come. Wait a second.
Wait a second, please. Microphone. It will not be heard.
Because we can use, for example, the profilers to see the memory leaks and analyze the performance of our language, and usually they are built in IDEs. So what's the difference in the tools you are using, and what is the advantage it brings?
Okay, thank you. Thank you for your question. With profilers are quite narrow area tools. They're providing limited set of metrics which they could collect actually. Memory leaks is one of the most obvious things, but as I have showed you in my presentation, we could have many different problems related to operating system itself. Leaking IOPS is just one. Leaking CPU profiler, which will show you leaking CPU. Okay, you could collect CPU load. Most of profilers could provide you with this. But for example, I/O. For example, threads could be handled. It's the matter of general usage and narrow usage. If you are 100% sure that your application will not introduce any unknown behavior to operating system, you could use profiler, because profiler will be analyzing your applications in quite a little bit smaller area. Black box performance analysis from operating system perspective will show you a more general picture. So this is why I recommend not to limit your testing only to profilers. Because, and also profiler mostly useful during lifetime of your application. And for example, you will not see what happened to operating system after your application exited, after your application maybe crashed, after your application have closed main process and started some childs. So operating system knows all about this, and in this case, it will be showing a little bit bigger picture than profilers. That's why.
Do we have any further questions? Okay, we have one.
Hello, thanks for your speech. I've got another question related to baseline, I think. I'm wondering, and I can see some kind of risk with choosing the baseline. I understand that if we know that our program is on the level that we know that there is everything okay, we have a release version, and we can use this program as a baseline, it's okay, but what if we are producing the program for many operating systems and we don't know which version of our program could be the baseline version? So we need to check our program, I think, all operating system that we are compiling our program for, yeah? So how you are choosing this operating system and how you are choosing this baseline? Because the question is, because I can see the risk if you choose the wrong baseline, I mean the wrong operating system or wrong version, and on some level of testing you will see that there is the leak of something, and you cannot compare this to some other results because you are comparing this to the baseline, and on some level you don't know if there is the problem with the application or there is a problem on the operating system. So if the real question is if you have many baselines to compare baseline between, or some more tests to have this comparison.
Great question, thank you. we have this situation in our organization. We're testing mostly for end user applications. We're having Windows 7, which is quite old, and we're migrating to Windows 2016 Terminal Edition, and we are migrating to Windows 10, and we're having and this operating system behaving differently in different situation. What we are doing inside of one operating system, because even for one operating system we have different environments. We have VDI, we have workstations, we have server side. We're testing for each operating system. So, for example, we're having Windows 7 and Windows 7 deployed in different environments. Workstations, VDI, some maybe laptops. We're choosing the most sensitive environment for this operating system. In our case, it's VDI because it's aggregation, it's contention, and when your program is leaking in by some means in your own workstations, it's one thing. But when it's leaking on VDI, when have consolidated many leaking on one physical servers, you could have problems quite quickly, quicker. So my advice is to do baseline collection for every operating systems, but for one operating systems you need to choose most sensitive. It's more limited by resources, most likely, or maybe you have something like critical zone users and just take their configuration. That's our approach, which we are using actually. So test each operation system, but choose most sensitive configuration inside of all the variety inside one operating system. Thank you. More question?
Two questions. The first one: how often should we perform this black box analysis? And the second is more about high performance computing. Do you check, or should we check, the performance of the application for the same system but for different hardware configuration? And should we focus also on some low details like CPU, cache misses, or should we take care about these features on lower level of tests?
Could you please explain what you understand under high performance calculations, because it could be different.
So actually your talk was mostly focused on memory leakage, I/O leakage, and interaction between system and the user application. But for example, let me assume that I'm working for some artificial intelligence AI program, and I have a lot of loop and a lot of that data, and in that case I don't have a lot of I/O operation, but I have a lot of calculations, and the cache, CPU cache, and efficiency of the cache usage is for this program more important than a simply I/O operation. And that's why I'm wondering...
Is it running on one node or many nodes?
Let me assume for one node.
For one node, okay.
So should we take care about these issues on the black box, or should we perform, for example, should we profile our application and focus only on data processing function, like unit test or something like that?
Okay, thank you. Great question. First, how often should we do? In our world, when we are having 100 deliveries per day, 100 releases per day, it's quite hard to do quite often, because this is quite time consuming. We are dealing with quite normal waterfall process when delivery is done in monthly cycles. So we're releasing one versions once a month. In this case, for us, it's much simpler, and we could test each version which we are delivering. In situations which you are delivering several times a day, several times a week, it could be quite hard. In this case, you could choose some compromise. So test only minor versions, test only some features when some features are released, or every 2 weeks, for example. We have another project which is delivering quite often, and we are doing longer captures, not 24 hours captures, but 72 hours captures, just on a regular basis. We are not receiving new version of applications, we're just collecting all the metrics and seeing what is going on. Is it okay, is it not okay? We're not producing reports, we're not producing releases, we're just looking how it's going on. In this case, it could help in this case. For high performance, you're talking more about application-specific performance. What I'm talking here is more general performance. Performance, what is will be visible when it's too late, for example. For your approach, you need to do some analysis inside your applications, because you know how your application is working and what you really need. You could do a lot of stuff during black box performance analysis as well, because cache hit or miss, memory paging, and something like that, you could collect this. But in this case, profilers will be, I believe, more useful for you, because you want to understand performance of some small part of your code, not all the application itself. All application itself could be also analyzed as black box performance, because you could find something which you have never anticipated in your program. Maybe it's creating some another problems. And your specific performance should be done during your development stages, refactoring stages, profiling stages. So I propose you to split these operations. Any more questions?
I've got one more question. I promise that will be the last question from my side. This is the question about the results of your analysis that you are providing to managers, to software developers, and all people. The question is if you have any targets of the results. I mean, how you are preparing your test scenarios, if you are using some requirements for the software, and how do you know what numbers are the good numbers? I'm not thinking about baseline, I'm thinking about the results. How do you know that, and who is preparing the test scenarios, if it's only you, or if you are preparing this targets and these scenarios together with someone?
Thank you. Where do we get test scenarios? We are getting it, of course, from developers, from business analytics, from product owners. We asking them to provide us with most common user operations. Once again, if your application have some feature which is used like once a month, twice a month, there is no point to analyze its performance, because even if it's just sending results to you as a developer, or some aggregated statistics which is used once a month, there is no point to engage it in normal black box performance analysis. We are analyzing only most common used operations, what is used on daily basis, on hourly basis, not even on weekly basis. So if it's used quite often, we are including it. If your application is engaging some other applications, interacting with some other applications in operating systems, we also testing these applications, and most likely we already know how to test it. For example, once again, if you are developing a session for Chrome browser, you already know how Chrome browser works. You need to open tab, you need to open some page and look how it's loading. You need to open another tab, load another page, reset to about blank, for example, and repeat several times. Who receiving our reports? In my organization, before our team was created, it was a little bit chaotic. Everyone could develop and deliver everything to servers, desktops, mostly desktops. There were a lot of different teams developing absolutely different programs, and they all want our users to have it for sure, because one user in an organization uses this and all others should have it. And at some point, users started to cry, going to their managers, asking managers to go to higher managers, and finally CIO created our team to prevent people delivering good software from good developers, but with some unpredictable features. So now we could veto any release delivery to end user workstations because of performance problems. So our reports is going directly to developers. If it's okay or not okay, we have currently only 2 states. You are pass, you not pass. Previously it was like, oh, we are allowing you to pass, but please fix this. Now anymore, no. Just pass, not pass. And we are aggregating all the information and sending it to higher management just to a little bit brag ourselves and showing that, oh, guys, we have saved our organization from these sufferings and to show that we are earning our bread not for free. Thank you.
I think we can conclude this session, as I don't see any other volunteers or questions. Okay, please give a big round of applause for Dmitry. Thank you very much for attending Code Dive Day 1, and I invite you to attend Code Dive Day 2. See you tomorrow.
Thank you, thank you. Have a nice evening, bye.